The first thing that dissolves when an orca enters the frame is the idea of randomness. Nothing about the animal's movement suggests improvisation or simple reaction. The water around it is not empty space, but a structured environment filled with currents, pressure gradients, sound pathways, and escape routes that the animal reads with the precision of a seasoned navigator. An orca does not simply hunt within an ecosystem. It reorganizes that ecosystem temporarily around itself, bending the behavior of prey species, the movement of water, and even the reactions of other predators through presence alone. From the moment a pod aligns its direction, spacing, and depth, the hunt becomes less an act of pursuit and more a coordinated operation unfolding across multiple dimensions of the marine environment. The pod moves as a distributed unit rather than a cluster of individuals, maintaining deliberate distances that allow each member to perform a distinct function without interfering with the acoustic or hydrodynamic signals of the others. Some individuals take forward positions, scanning ahead with echolocation pulses tuned for range rather than detail, while others remain flanking or slightly behind, reading the echoes bouncing off prey schools or ice edges from alternative angles. This division of roles is not fixed by age or sex alone, but adjusts dynamically based on the target species, environmental conditions, and even recent success or failure in similar hunts. The ocean becomes a tactical map in motion, with each orca updating its position not only in response to prey, but in constant reference to the movements and signals of its pod mates. When prey is located, the pod rarely commits immediately. Instead, it begins a phase of information gathering that resembles reconnaissance more than attack. Orcas reduce vocal output to limit detection, switching from active echolocation to passive listening when necessary, exploiting the fact that many prey species generate noise through movement, respiration, or panic responses. This restraint reveals an understanding of sensory trade-offs, as echolocation provides detailed information but also broadcasts presence, while silence preserves ambiguity. During this phase, individuals may test prey reactions through subtle pressure waves generated by body rolls or tail flicks, gauging cohesion and alertness without triggering full flight. The prey, unaware that it is already surrounded by assessment rather than pursuit, continues to behave normally, unaware that the outcome has been largely decided. Once the pod commits, the hunt unfolds through deliberate sequencing rather than brute force. One or two individuals may initiate contact, driving prey toward a predetermined boundary such as shallow water, an ice shelf, or the surface layer where maneuverability is reduced. These lead orcas are not attempting capture themselves, but acting as drivers, exploiting prey escape instincts that funnel them toward less favorable terrain. Meanwhile, other pod members hold back, conserving energy and positioning themselves at critical interception points. Timing is essential, as premature acceleration by any individual can scatter prey unpredictably, while delayed movement allows escape routes to reopen. The coordination required to maintain this balance speaks to a shared understanding of cause and effect, developed through repeated experience rather than hardwired reflex. In hunts involving schooling fish, the strategy becomes even more layered. Orcas may herd fish into dense bait balls, using synchronized tail slaps and bubble curtains, manipulating water movement to create physical and sensory barriers. The bubbles are not random turbulence, but a calculated tool, as many fish interpret rising bubbles as solid obstacles due to their reflective properties and the way they disrupt visual and lateral line cues. By tightening the school, the orcas reduce individual escape probability and increase capture efficiency, allowing multiple pod members to feed without excessive exertion. Even within this apparent chaos, individuals maintain spacing and take turns striking the school, avoiding collision and minimizing wasted effort. The hunt becomes a rotating system rather than a free-for-all, maximizing return while preserving pod cohesion. More striking still are hunts that involve large, dangerous prey, such as seals, sea lions, or even other cetaceans. In these scenarios, orcas demonstrate an ability to model prey perception and exploit psychological thresholds. When hunting seals resting on ice floes, certain pods have learned to generate coordinated waves that destabilize the ice, washing the prey into the water without direct contact. This behavior requires precise alignment of multiple individuals, synchronized swimming speed, and timing that accounts for wave interference patterns, all while maintaining enough distance to avoid injury from ice fragments. The seals are not overpowered, but outmaneuvered by an understanding of physics and fear responses, as the sudden loss of stable footing triggers panic that the orcas exploit in the water. What elevates these strategies beyond instinct is their variability across populations. Orcas in different regions do not hunt the same way, even when encountering similar prey, because techniques are not genetically fixed, but culturally transmitted. Some pods specialize in fish, others in marine mammals, and still others in specific prey types such as rays or sharks, each requiring distinct tactics and risk assessments. These specializations are learned over time, passed from older individuals to younger ones through observation, participation, and gradual role assumption. A juvenile orca does not emerge with a complete hunting repertoire, but acquires it through years of exposure, learning not only how to execute techniques, but when to abandon them under changing conditions. This cultural transmission creates traditions that persist across generations, shaping pod identity as strongly as genetics. Certain vocalizations used during hunts, for example, are unique to specific populations and serve both as coordination tools and as markers of group membership. These calls are learned rather than innate, reinforcing the idea that orca societies function as knowledge networks rather than instinctive collectives. When a pod develops a successful technique, it becomes part of the group's behavioral library, refined through repetition and adapted to new contexts. Failure is not merely tolerated, but instructive, as unsuccessful hunts provide information that influences future decisions and strategy adjustments. The cognitive demands of such systems are immense, requiring memory, foresight, and the ability to infer the intentions of both prey and podmates. Orcas must track multiple variables simultaneously, including prey movement, environmental constraints, and the positions of other hunters, all while adjusting speed and depth in three-dimensional space. This level of coordination suggests not only advanced intelligence, but an ecological niche built around that intelligence, where survival depends as much on learning and cooperation as on physical attributes. The ocean, vast and often resource-sparse, rewards those who can reduce uncertainty through shared knowledge and collective action. Even the aftermath of a hunt reflects this social structure. Food sharing is common, particularly involving calves or older individuals, reinforcing bonds and ensuring knowledge holders remain healthy and present within the pod. This redistribution of resources strengthens group resilience, allowing pods to survive fluctuations in prey availability that would devastate solitary predators. In this sense, orca hunting is not simply about immediate caloric gain, but about sustaining a long-term social system that amplifies individual capabilities through collective memory. Seen in this light, the orca is less a solitary apex predator and more a mobile command unit, operating within a fluid environment that demands adaptability and foresight. Each hunt is a demonstration of accumulated knowledge, refined over generations and executed with precision that rivals human coordinated activity, yet remains entirely rooted in natural processes. The strategies employed are not abstract plans, but embodied intelligence, expressed through muscle, sound, and motion, shaped by the relentless feedback of success and failure in an unforgiving environment. To watch an orca hunt is to witness the ocean thinking through flesh and water, revealing a form of tactical genius that challenges assumptions about the limits of non-human cognition and underscores the profound complexity embedded within marine ecosystems. The ocean surface above a feeding humpback whale often looks deceptively calm, a broad plain of light broken only by faint ripples and drifting foam. But below that surface, the water is being reshaped into a temporary architecture, assembled with precision and intention rather than brute strength. A bubble net is not an explosion of motion or a chaotic feeding frenzy. It is a constructed space, built out of air, sound, pressure, and fear, designed to alter how prey perceives its environment and how water itself behaves. To understand this strategy is to abandon the idea of whales as simple giants that overpower food through size alone, and instead recognize them as engineers working within the physical laws of fluids and animal psychology. The process begins long before bubbles appear. A group of humpbacks descends together, spreading out beneath a school of small fish such as herring or krill that has risen toward the upper layers of the ocean. These prey species occupy this zone because light fuels plankton growth, which in turn attracts the fish, creating a vertical stacking of life that predators learn to exploit. The whales position themselves with deliberate spacing, each individual aware of the others through sound, body orientation, and subtle changes in water movement. Their massive bodies displace water in slow, controlled arcs, minimizing turbulence that might scatter the prey prematurely. This early phase is about containment rather than capture, as the whales establish the boundaries of an invisible arena. Once positioned, one or more whales begins releasing streams of bubbles while swimming in a tightening spiral beneath the prey. These bubbles rise rapidly due to buoyancy, forming a vertical curtain that expands upward and outward as it ascends. For a human observer, bubbles seem insubstantial, fragile, and easily ignored. But for small fish, they represent a complex sensory barrier. Bubbles scatter light, distort visual cues, disrupt the lateral line system that fish use to sense pressure changes, and produce sound frequencies that many prey species interpret as danger. Fish instinctively avoid penetrating bubble fields because they cannot easily judge what lies beyond them, and because the turbulence interferes with coordinated schooling behavior. As the spiral grows, the fish are not physically blocked, but psychologically constrained, compressed inward by an expanding ring of perceived threat. The geometry of the spiral is critical. A circular or helical bubble net creates a continuously closing boundary, unlike a straight line of bubbles that fish could simply swim around. As the whale ascends in a spiral, the diameter gradually decreases, tightening the net and forcing the prey into a dense aggregation near the center. This increasing density is not accidental. It dramatically alters the energetic balance of the hunt. Fish packed tightly together interfere with each other's movement, collide more frequently, and struggle to maintain orientation, making them far easier to capture in bulk. At the same time, the density amplifies the effectiveness of the whale's next move, transforming a dispersed resource into a concentrated one. Sound plays a parallel role in this construction. Some humpbacks produce loud, low-frequency vocalizations during the bubble net formation, adding an acoustic wall to the visual and tactile barrier created by the bubbles. These sounds propagate efficiently through water and can disorient prey, further reinforcing the net's containment effect. The combination of bubbles and sound creates a multisensory trap, exploiting the prey's reliance on predictable environmental cues. Rather than chasing individual fish, the whales manipulate the prey's perception of space itself, turning open water into a shrinking chamber with no obvious exit. Coordination among the whales reaches its peak during this phase. Individuals must synchronize depth, speed, and bubble release timing to ensure the net forms evenly and does not collapse prematurely. If one whale ascends too quickly or releases bubbles unevenly, gaps can form that allow prey to escape. This demands a shared understanding of the plan and constant adjustment based on real-time feedback. Young whales learn these techniques through observation and participation, gradually assuming more complex roles as they mature. The skill involved is not encoded fully at birth, but refined through practice, making bubble net feeding a cultural behavior passed down through generations rather than a simple instinctual response. Once the net is complete and the prey compressed, the whales transition from builders to harvesters. Several individuals align beneath the concentrated fishball, orienting their bodies vertically with mouths closed. In a moment of near-perfect timing, they surge upward through the center of the net, opening their jaws at the last instant to engulf massive volumes of water and prey. This ascent is powerful but brief, relying on the work already done by the bubble net to ensure success. The whale's baleen plates act as filters, allowing water to escape while trapping fish inside the mouth. The effectiveness of this lunge depends entirely on the density created by the net. Without it, the energy cost of capturing enough prey would be far higher. What makes this strategy remarkable is how it externalizes effort. Rather than expending continuous energy in pursuit, the whales invest in constructing a trap that does much of the work for them. The rising bubbles maintain the barrier passively once released, and the prey's own behavior keeps them contained. This approach reflects a deep alignment between the whale's physiology and their environment. Humpbacks possess large lungs capable of releasing substantial volumes of air, and their ability to control buoyancy and movement in 3 dimensions allows precise placement of the net. The ocean's physical properties, from buoyancy to sound transmission, become tools rather than obstacles. The ecological implications extend beyond the immediate hunt. By feeding in this manner, humpbacks influence the distribution and behavior of prey species, shaping how fish schools form and move in response to predation risk. Over time, these interactions can affect nutrient cycling and energy flow within the marine ecosystem, as concentrated feeding events redistribute biomass and stimulate localized productivity. The whales are not merely consumers, but active participants in structuring the dynamics of their environment, their behavior rippling outward through the food web. Bubble net feeding also illustrates the role of innovation in animal survival. This technique is not universal among humpbacks, appearing primarily in certain populations where environmental conditions and social learning support its development. In regions where prey species respond strongly to bubbles and sound, the strategy thrives. Elsewhere, whales rely on different methods. This variability underscores the importance of flexibility and learning in long-lived species, where individuals can accumulate experience and adapt behavior to local conditions. The ocean is not a uniform space, and successful predators must tailor their approaches accordingly. Watching a bubble net hunt unfold reveals a form of intelligence that is situational rather than abstract, expressed through movement, timing, and environmental manipulation rather than tools or symbols. The whales do not dominate the ocean through size alone, but through an ability to read and reshape the rules governing their prey. Each bubble released is a small act of construction, contributing to a larger structure that exists only briefly before dissolving back into open water. In that fleeting moment, the whales demonstrate how understanding physics and behavior can transform vulnerability into abundance, turning air into architecture and coordination into sustenance. At the surface, a sperm whale appears almost unfinished, a blunt-headed silhouette drifting in slow arcs through sunlit water, its massive body barely hinting at the extreme environment it is built to endure. The ocean around it feels familiar at this level, a place of light penetration, drifting plankton, and gentle thermal gradients. But this familiarity is an illusion that dissolves the moment the whale begins to descend. With a subtle tilt of its body and a controlled release of air, the animal commits itself to a vertical journey that will take it far beyond the reach of sunlight, into a realm defined not by color or shape, but by pressure, cold, and sound. This is not a brief foray, but a transition into a different physical world, one where the rules that govern human experience lose their relevance. As the whale sinks, the water darkens rapidly, and temperature drops with depth, creating layers that would challenge most large mammals. The sperm whale meets these gradients with a physiology engineered not for speed or agility, but for endurance under crushing conditions. Its muscles are saturated with myoglobin, a protein that binds oxygen with remarkable efficiency, giving the tissue a dark, almost black coloration. This adaptation allows the whale to store vast reserves of oxygen directly within its muscles, rather than relying solely on the lungs or bloodstream. As depth increases and breathing becomes impossible, these internal reserves sustain cellular respiration long after surface oxygen would have been depleted in less specialized animals. The descent is deliberate, not rushed, as the whale manages its oxygen economy with careful precision. Heart rate slows dramatically, a response known as bradycardia, reducing oxygen consumption by limiting blood flow to non-essential tissues. Peripheral blood vessels constrict, prioritizing oxygen delivery to the brain and heart, while muscles switch partially to anaerobic metabolism when necessary. This redistribution is not a sign of stress, but a controlled state that allows the whale to stretch each molecule of oxygen across an extended dive. Even the lungs participate in this strategy, collapsing safely under pressure to prevent nitrogen absorption that would otherwise cause decompression sickness, a danger that defines the limits of human diving. Pressure increases relentlessly as the whale passes into the mesopelagic and then bathypelagic zones, where each additional depth increment adds immense force to every surface of the body. In humans, Such pressure would crush air-filled spaces and disrupt cellular integrity, but the sperm whale's anatomy minimizes these vulnerabilities. Flexible rib cages allow the chest to compress without damage, while air spaces in the skull are reinforced or filled with oil, like substances that resist compression. The spermaceti organ, a large mass of waxy oil in the head, plays a role not only in sound production, but also in buoyancy regulation, changing density as temperature and pressure vary, subtly assisting the whale's vertical movement through the water column. As light fades completely, vision becomes irrelevant, replaced by a sensory landscape built entirely from sound. In this darkness, the sperm whale emits powerful clicks that reverberate through the water, traveling vast distances before bouncing off objects and returning as echoes. These clicks are among the loudest biological sounds on the planet, focused into a narrow beam that allows the whale to scan the environment with extraordinary resolution. The returning echoes provide information about size, distance, texture, and movement, effectively constructing a three-dimensional acoustic map of the surroundings. In this world, sound is not merely a signal, but a form of perception that substitutes for sight entirely. Prey detection at these depths requires more than simple location. It demands interpretation of subtle acoustic cues in an environment filled with noise from currents, shifting thermal layers, and the faint movements of other organisms. Many of the whale's preferred prey, such as large squid, are themselves adapted to darkness, relying on stealth and sudden bursts of motion to avoid predators. The whale counters this with sustained echolocation, tracking prey through evasive maneuvers and adjusting its approach based on echo changes that reveal acceleration or directional shifts. Each click is both a probe and a commitment, expending energy that must be balanced against oxygen reserves, reinforcing the need for efficiency rather than prolonged pursuit. When contact is made, the encounter unfolds slowly, almost cautiously, as the whale closes the final distance. Unlike surface predators that rely on explosive speed, the sperm whale's strategy emphasizes reach and control. Its jaws, lined with large conical teeth, are designed to grasp rather than slice, securing prey that may be as long as the whale's own body width. The struggle, if it occurs, is brief, as the whale's mass and momentum overwhelm most resistance. In this silent darkness, there is no visual drama, only the tactile exchange of force and the faint acoustic signatures of movement, all filtered through the whale's sensory system. Throughout the hunt, the whale's body remains under extreme physiological strain, operating near the limits of what mammalian biology can sustain. Blood chemistry shifts as carbon dioxide accumulates and pH levels change, yet the whale's tissues tolerate these fluctuations without triggering the panic responses seen in less adapted species. Enzymatic pathways are tuned to function under low oxygen conditions, and protective mechanisms reduce oxidative damage when normal circulation resumes at the surface. These adaptations reflect an evolutionary history shaped by repeated exposure to extremes, where survival favored individuals capable of maintaining cellular stability under conditions that would incapacitate or kill others. The ascent begins only when the whale's internal calculations signal that oxygen reserves are nearing their limits. Unlike the descent, which is passive and controlled, the return to the surface requires active effort, swimming upward against increasing buoyancy as pressure decreases. Blood flow gradually normalizes, and the heart rate increases in stages to prevent sudden shifts that could damage tissues. Even during this phase, the whale remains vigilant, using echolocation to navigate through layers of water that may contain other predators or obstacles. The surface, when it finally reappears, is not a relief, but a transition back into a familiar state, marked by a powerful exhalation that expels spent air and resets the system for the next dive. What makes this cycle extraordinary is not any single adaptation, but the integration of all of them into a coherent survival strategy. Oxygen storage, cardiovascular control, pressure tolerance, and sensory specialization do not operate independently, but as parts of a unified system tuned for life in a place beyond human reach. The depths the sperm whale inhabits are regions we can barely access, even with advanced technology, requiring heavy equipment, artificial atmospheres, and strict time limits to avoid fatal injury. For the whale, these depths are not hostile but routine, navigated with a competence that renders their dangers almost invisible. This reality challenges human assumptions about intelligence and adaptation, as the whale's mastery of the deep is not the result of conscious engineering, but of evolutionary refinement across countless generations. The animal does not understand pressure or oxygen in abstract terms, yet its body embodies solutions to problems we still struggle to model accurately. Even our most advanced simulations fail to capture the full complexity of the environment the whale experiences, as sound behaves differently at depth. Chemical gradients shift unpredictably, and biological interactions occur on scales that resist easy measurement. In framing the sperm whale as a living pressure tank, it becomes clear that its true habitat is not the surface ocean we see, but the vast, dark interior that lies beneath. Each dive is a descent into a world defined by forces that dwarf human experience, a place where survival depends on precision, restraint, and an intimate relationship with the physical properties of water. The whale does not conquer this world through dominance, but through compatibility, its physiology aligning so closely with its environment that the boundary between organism and ecosystem seems to blur. In watching a sperm whale disappear into the depths, we are not witnessing a simple dive, but the activation of a biological system optimized for a realm we can barely imagine, let alone inhabit. The presence of a blue whale alters the ocean before it ever feeds, not through aggression or speed, but through scale alone, as its body displaces water on a level that few other living systems can match. To encounter one is to sense the ocean bending slightly around a moving mass, currents shifting, plankton layers disturbed, and smaller animals reacting to pressure changes long before the whale itself becomes visible. At the surface, the animal appears almost impossibly large, a moving continent of muscle and bone whose slow, deliberate motion seems incompatible with the fragile organisms it depends on for survival. This apparent contradiction is not a flaw in the system, but a demonstration of how the ocean's energy flows obey a mathematics that feels counterintuitive to land-based intuition. The blue whale's world is structured by abundance at small scales and scarcity at large ones. The prey it targets, primarily krill, are tiny crustaceans that individually contain very little energy, yet collectively form dense, drifting clouds that can stretch for kilometers and pulse with life as they follow phytoplankton blooms. These blooms are fueled by sunlight, nutrients, and seasonal upwelling, creating vertical highways of productivity that rise and fall through the water column. The whale does not hunt krill as individuals, but engages with these vast aggregations as a resource field, much like a grazing animal interacts with a meadow rather than a single blade of grass. Survival at this scale depends not on precision targeting but on the ability to process enormous volumes efficiently. Lunge feeding is the core of this strategy, and it represents one of the most extreme biomechanical solutions to energy acquisition found in any animal. As the whale approaches a krill swarm, it accelerates despite its immense mass, converting stored momentum into forward motion that opens a mouth capable of engulfing a volume of water larger than the whale's own body. This is made possible by expandable throat pleats, long folds of tissue that run from the chin to the navel and unfold like an accordion under pressure. These pleats are not passive skin, but reinforced, elastic structures that distribute stress evenly, allowing the mouth cavity to balloon outward without tearing or collapsing. The act of engulfment is brief but mechanically intense. Water rushes into the mouth at high speed, carrying krill along with it, while the whale's lower jaw rotates downward and outward to accommodate the influx. This movement places enormous strain on the jaw joints, tongue, and ventral tissues, which are supported by specialized connective structures evolved to withstand repeated loading. The tongue itself, weighing as much as a large terrestrial animal, acts as both a piston and a gate, controlling water flow during the subsequent filtering phase. For a moment, the whale becomes a living container, holding a mass of water and prey that would overwhelm almost any other organism. Once the mouth is full, the whale closes its jaws and begins to expel water through baleen plates that line the upper jaw. These plates, made of keratin, form a flexible sieve that traps krill while allowing water to escape. The process is slow and controlled, relying on muscular contraction and the elasticity of the pleats to push water outward without losing prey. Filtering at this scale is not delicate but methodical, balancing the need to retain energy-rich organisms against the physical effort required to process such volumes. Each successful lunge can yield millions of individual prey, transforming a brief, intense action into a substantial caloric gain. The efficiency of this system lies not only in its size, but in its timing. Blue whales feed primarily during seasons when krill densities peak, aligning their migrations with cycles of productivity driven by temperature, light, and nutrient availability. During these feeding periods, the whales consume extraordinary amounts of food, building fat reserves that sustain them through long migrations and extended fasting. This strategy reflects a deep integration with oceanic rhythms, as the whales' movements trace the invisible contours of plankton blooms across entire basins. Their massive bodies are not liabilities, but storage devices, engines designed to convert short bursts of abundance into long-term survival. The energetic math of this lifestyle is unforgiving. Each lunge requires significant energy to accelerate and overcome drag, making efficiency critical. Studies of blue whale feeding behavior reveal that the whales selectively target the densest krill patches, often diving repeatedly through the same layer to maximize return on effort. This selectivity is guided by sensory cues that include vision in low light, mechanoreception, and possibly acoustic feedback from prey movement. The whales are not indiscriminate vacuum cleaners, but informed foragers that assess prey density before committing to the costly act of engulfment. This feeding strategy has profound ecological consequences. By consuming vast quantities of krill, blue whales influence the distribution of nutrients through their waste, which is rich in iron and other elements essential for phytoplankton growth. These nutrient plumes fertilize surface waters, stimulating primary production that supports the very food webs the whales depend on. In this way, the whales act as mobile nutrient recyclers, linking deep feeding zones with sunlit surface layers. Their presence enhances ecosystem productivity rather than depleting it, illustrating a feedback loop where size amplifies rather than disrupts balance. The contrast between the whale's immense body and its tiny prey highlights the strange arithmetic of the ocean, where energy is concentrated at microscopic scales and only accessible to giants through extreme adaptations. On land, large animals typically feed on large plants or prey, but the ocean inverts this relationship, allowing the largest animals that have ever lived to subsist on some of the smallest. This inversion is made possible by the fluid medium, which supports body mass and enables filter feeding strategies that would collapse under gravity and air. Water, with its density and resistance, becomes both the challenge and the solution, shaping the whale's anatomy and behavior. The blue whale's physiology reflects this integration with water at every level. Its heart, the largest of any animal, pumps blood through an extensive network of vessels that deliver oxygen to tissues during feeding bursts and long dives. Its muscles are adapted for sustained power rather than rapid acceleration, supporting repeated lunges without exhaustion. Even its skin, smooth and streamlined, reduces drag during movement, conserving energy across long distances. Every aspect of the animal contributes to the efficiency of an engine built not for speed or combat, but for throughput, converting planktonic biomass into motion, migration, and reproduction. Despite this efficiency, the system remains vulnerable to disruption. Changes in ocean temperature, acidification, and nutrient cycles can alter krill distribution, breaking the link between whale migrations and prey availability. Because blue whales depend on dense aggregations rather than scattered individuals, even small shifts in productivity can have outsized effects on feeding success. This sensitivity underscores the precision of the system, where extreme specialization yields incredible efficiency under stable conditions, but leaves little margin for error when those conditions change. Watching a blue whale feed is to witness a process that feels almost industrial in scale, yet entirely organic in execution. The whale does not chase or fight, but opens itself to the ocean, temporarily becoming part of the water column as it filters life from the flow. Each lunge is a calculation expressed through muscle and motion, a response to a resource field measured not in individuals but in density gradients and energy returns. The whale's size, often perceived as excess, is in fact the minimum required to make this strategy viable, a threshold beyond which the ocean's strange mathematics begin to work in its favor. In framing the blue whale as the biggest engine on Earth, it becomes clear that its true power lies not in dominance, but in alignment with ecological processes that operate at massive scales. The animal embodies a solution to a problem defined by abundance and dispersion, using bulk and biomechanics to bridge the gap between microscopic prey and macroscopic survival. Its existence challenges assumptions about efficiency, reminding us that in the ocean, success is often achieved not by narrowing focus but by expanding capacity, allowing the flow of life itself to pass through a body designed to harness it. In coastal shallows and open pelagic waters alike, dolphins move through an environment that is never empty to them, even when it appears visually uniform or opaque to an outside observer. The ocean, from their perspective, is a constantly updating three-dimensional map constructed from sound, pressure, and motion. A space where distance, texture, and intent are revealed not by light, but by echoes returning through water. When a dolphin swims forward, it is not entering the unknown, but actively generating information with every click it produces, illuminating its surroundings in pulses that travel outward, strike objects, and rebound with data encoded in time delay, frequency shift, and intensity. This sensory process does not merely supplement vision. It replaces it entirely in conditions where light fails, allowing dolphins to navigate, hunt, and cooperate within a living acoustic architecture. Echolocation begins in the nasal passages rather than the mouth, where specialized structures generate rapid sequences of high-frequency clicks that are focused forward through a fatty organ in the forehead known as the melon. This structure acts as an acoustic lens, shaping and directing sound waves into a narrow beam that can be aimed with subtle head movements. As the dolphin sweeps this beam across its environment, it samples space in fine increments, adjusting click rate and intensity depending on distance and complexity. Long-range exploration uses slower, more powerful clicks that travel farther, while close inspection relies on rapid, quieter pulses that build detailed images of nearby objects. The dolphin is not broadcasting blindly, but tailoring its signal to the task at hand, managing energy expenditure while maximizing informational return. When echoes return, they are received primarily through the lower jaw, which channels vibrations to the middle and inner ear via specialized fat-filled cavities that transmit sound efficiently. These echoes carry more than simple location data. They reveal the density, shape, and even internal structure of objects. A fish reflects sound differently than a rock, and a hollow object produces a distinct acoustic signature compared to a solid one. Moving prey alters the frequency of returning echoes through Doppler shifts, allowing dolphins to detect not only motion, but direction and speed. In this way, echolocation becomes a form of active perception that constructs a layered representation of the world, one that includes both static features and dynamic processes unfolding in real time. This acoustic vision operates continuously as dolphins travel, but it becomes especially refined during hunting. Schools of fish, which might appear as shimmering clouds to a human diver, present themselves to dolphins as complex acoustic landscapes filled with overlapping echoes and movement patterns. Individual fish are distinguishable within the mass, their relative positions tracked as the school shifts and compresses. Dolphins read these patterns instinctively, identifying weaknesses, escape routes, and moments when coordinated action will yield the greatest reward. The hunt begins not with a chase, but with assessment, as dolphins circle or approach from below, probing the school with sound while remaining just outside its defensive reactions. Cooperative hunting elevates this process from individual perception to shared strategy. In a pod, multiple dolphins synchronize their echolocation and movement, effectively expanding the sensory field beyond what any single animal could generate alone. One dolphin may take on the role of driver, using bursts of sound and physical presence to flush fish from cover or push them toward the surface. The fish respond to this pressure by tightening their formation or attempting to flee. reactions that are anticipated rather than surprising. Another dolphin positions itself ahead of the school, reading the acoustic chaos and selecting the optimal moment to intercept individuals that break formation. Timing is critical, as premature movement can scatter prey, while delayed action allows the school to reorganize and escape. This division of labor is fluid rather than rigid, with roles shifting based on opportunity and environmental context. Dolphins communicate through whistles and body language, coordinating movements without breaking acoustic scanning. The ocean becomes a shared workspace where information flows between individuals through sound and motion, enabling complex maneuvers that appear effortless but rely on constant feedback and adjustment. Even in turbid or dark water, where visibility drops to near zero, the hunt proceeds with precision, guided by an acoustic map that updates faster than vision ever could. The intelligence underlying this behavior is inseparable from the sensory system that supports it. Echolocation does not simply provide raw data. It allows dolphins to manipulate information actively, focusing on specific targets while filtering out irrelevant noise. This selectivity suggests a cognitive framework capable of prioritizing, predicting, and adapting based on experience. Dolphins learn the acoustic signatures of local prey species and habitats, refining their hunting techniques over time. In some regions, pods develop specialized strategies suited to particular environments, such as driving fish into shallow bays or against reef structures, demonstrating an ability to integrate environmental features into their acoustic models. Beyond hunting, echolocation shapes how dolphins interact with their surroundings in subtler ways. Navigation through complex habitats such as mangroves, coral reefs, or kelp forests requires constant awareness of obstacles and pathways that shift with tides and currents. Dolphins use sound to trace these environments, memorizing landmarks and routes that remain stable over time. Even social interactions are informed by acoustic perception, as individuals recognize each other by the unique qualities of returning echoes, reinforcing group cohesion in a medium where visual cues are often unreliable. The energetic cost of echolocation is carefully managed. Producing sound requires muscular effort and metabolic investment, particularly during prolonged hunts. Dolphins balance this cost by adjusting signal strength and duration, conserving energy when detailed scanning is unnecessary and intensifying output only when precision is required. This efficiency reflects an evolutionary trade-off that favors information-rich perception over constant high output, ensuring that echolocation remains sustainable across long foraging sessions and migrations. Environmental conditions influence how sound travels, adding another layer of complexity to the dolphin's acoustic world. Temperature gradients, salinity changes, and depth affect sound speed and direction, creating acoustic shadows and channels that can distort echoes. Dolphins account for these variables instinctively, modifying their scanning patterns to compensate for refraction and attenuation. In doing so, they demonstrate an embodied understanding of ocean physics, adjusting behavior based on how the medium itself shapes perception. The ocean is not a neutral backdrop, but an active participant in sensory experience, one that dolphins have learned to read and exploit. This reliance on sound also makes dolphins sensitive to changes in their acoustic environment. Natural noise from waves, rain, and other animals forms a baseline that dolphins incorporate into their perception. But human-generated noise introduces unpredictable interference that can mask echoes and disrupt communication. In noisy conditions, dolphins must increase signal intensity or alter frequencies, expending additional energy to maintain the same level of awareness. This adaptation highlights the finely tuned balance between sensory input and environmental stability that defines their way of life. Echolocation allows dolphins to experience the ocean as a place of depth and texture rather than emptiness. They perceive layers of information where humans perceive darkness, sensing the contours of the seafloor, the movement of distant animals, and the subtle shifts that signal opportunity or danger. This perception is immediate and continuous, a live scan that rebuilds the world with every click. It supports a form of intelligence grounded in interaction rather than abstraction, where understanding emerges from engagement with a dynamic environment. In cooperative hunts, This intelligence manifests as collective awareness, with each dolphin contributing to and benefiting from a shared sensory field. The success of the group depends not on dominance or hierarchy, but on coordination and trust, as individuals rely on each other's movements and signals to complete the hunt. This social dimension reinforces learning, as younger dolphins observe and participate, gradually acquiring the skills needed to navigate and hunt within the acoustic landscape. By framing dolphins as builders of a three-dimensional world through sound, it becomes clear that their intelligence is inseparable from their sensory adaptations. They do not simply react to stimuli, but actively construct a perception of reality that allows them to predict outcomes and adjust behavior accordingly. The ocean they inhabit is rich with information, constantly reshaped by sound waves and echoes that reveal patterns invisible to the eye. In this world, survival belongs to those who can listen deeply and respond with precision, and dolphins have evolved to do exactly that, transforming sound into sight and cooperation into sustenance within a medium that rewards those who can truly perceive it. In the cold, shifting waters, where light fractures quickly and visibility is often reduced to little more than suggestion, seals move with a confidence that seems disproportionate to what the eye can confirm. The ocean here is layered with currents, turbulence, and suspended particles that blur outlines and erase clear visual cues, yet the seal navigates this environment as though following marked paths. What appears to human perception as empty water is, to the seal, crowded with information lingering long after other animals have passed. This awareness does not come from sight or sound alone, but from a sensory system so refined that it turns motion itself into a readable record, allowing the animal to track prey that is no longer present and respond to events that have already faded from view. The key to this ability lies in the seal's vibrissae, the long, stiff whiskers that fan outward from the muzzle in graceful arcs. At a glance, they appear simple, even decorative, but their structure reveals a level of specialization rarely matched in the mammalian world. Each vibrissa is anchored deep within a follicle rich in nerve endings and blood vessels, forming a highly sensitive interface between the animal and the surrounding water. Unlike the whiskers of terrestrial mammals, which primarily detect direct contact, seal vibrissae are adapted to sense minute changes in water movement, translating fluid dynamics into neural signals that the brain interprets with astonishing precision. As a fish swims through water, it leaves behind a wake composed of swirling vortices and pressure differentials that persist for longer than one might expect. These disturbances are shaped by the fish's size, speed, and swimming style, forming a unique hydrodynamic signature that slowly dissipates but does not vanish immediately. To most predators, this wake is irrelevant, a transient phenomenon lost in the background noise of moving water. To a seal, it is an invisible trail, a ghostly path that can be followed minutes after the prey has passed, even in complete darkness or murky conditions where vision offers no guidance. The vibrissae themselves are uniquely shaped to support this function. Rather than being smooth cylinders, they possess an undulating beaded profile along their length. This geometry reduces self-induced vibration as water flows past, preventing the whiskers from generating noise that would mask external signals. In effect, the seal's whiskers are engineered to remain quiet in motion, allowing them to register only the disturbances created by other moving objects. This refinement is critical, as the signals they detect are extraordinarily subtle, often involving shifts in water velocity measured in fractions that would escape most sensory systems entirely. When a seal enters a hunting mode, it often adopts a posture that maximizes whisker exposure, extending the vibrissae forward and slightly outward as it glides through the water. The animal's body remains streamlined and still, minimizing turbulence generated by its own movement. In this state, the seal becomes a living sensor array, sampling the water column for patterns that indicate recent activity. As the whiskers encounter a wake, they bend and vibrate in specific ways that encode information about direction and intensity. The seal's nervous system processes these signals rapidly, reconstructing the path of the prey, as though reading a map drawn in motion. Following such a trail requires more than sensitivity. It demands interpretation and memory. The seal must distinguish between wakes created by prey and those generated by currents, waves, or other animals. This discrimination is achieved through experience, as the seal learns the characteristic signatures of different species and behaviors. A fast, darting fish leaves a different pattern than a slow, cruising one, and a panicked escape creates turbulence distinct from routine movement. Over time, the seal builds an internal library of hydrodynamic cues, allowing it to prioritize certain trails while ignoring others that lead nowhere. As the seal advances along a wake, it constantly adjusts its course, making fine-scale corrections that keep it aligned with the invisible path. This tracking can continue even as the wake weakens, requiring the seal to extrapolate from incomplete information. The process resembles following a scent trail that fades with distance, except that here the medium is water and the cues are physical rather than chemical. In this sense, the seal's whisker-based perception occupies a unique sensory niche, bridging the gap between touch and remote sensing in a way that few other animals achieve. This ability transforms the dynamics of predator-prey interactions beneath the surface. Fish that rely on camouflage or rapid bursts of speed to escape visual predators find themselves vulnerable to a hunter that does not need to see them. Even in complete darkness, such as during polar nights or deep dives, seals can locate prey by tracing the echoes of their movement. The ocean becomes a space where hiding is not enough, as every action leaves a trace that can be read by those equipped to do so. The efficiency of this system has important energetic implications. Hunting by wake tracking reduces the need for prolonged chases, which would be costly in cold water, where heat loss is constant. Seals are endothermic animals that must maintain a stable internal temperature despite living in environments that rapidly draw heat away. By locating prey quickly and directly, they conserve energy that would otherwise be spent on extended pursuit. This conservation is supported by their thick blubber layer, which insulates the body and serves as an energy reserve, but behavioral efficiency remains a crucial component of survival. Thermoregulation and sensory adaptation are tightly linked in this context. Cold water increases density and slows the dissipation of wakes, effectively extending the lifespan of hydrodynamic trails. In polar and subpolar regions, where many seal species thrive, this physical property of water enhances the effectiveness of whisker-based tracking. The environment itself amplifies the seal's sensory advantage, creating a feedback loop where physiology and habitat reinforce one another. What might seem like a marginal adaptation in warmer waters becomes a dominant hunting strategy. In the cold, turbulent seas, seals often inhabit. The vibrissae also play a role in navigation beyond hunting. Seals moving through complex environments such as ice flows, rocky coastlines, or kelp forests use their whiskers to detect obstacles and flow patterns that indicate safe passage. Subtle changes in current direction can reveal the presence of solid structures or narrow channels, guiding movement even when visibility is compromised. In this way, the whiskers extend the seal's awareness beyond immediate contact, allowing it to read the environment through indirect cues. Young seals learn to use this sensory system gradually, refining their ability through play and exploration. Juveniles are often observed investigating wakes created by moving objects, including other seals or drifting debris, seemingly practicing the interpretation of hydrodynamic signals. This learning process suggests that while the vibrissae provide the raw sensory input, effective use depends on neural development and experience. Mastery of wake tracking emerges over time, shaped by repeated encounters and feedback from successful or failed hunts. The concept of tracking ghosts through water captures the essence of this ability, as seals pursue not the prey itself, but the memory of its movement preserved in fluid form. These ghost trails are ephemeral, constantly degrading as currents mix and dissipate energy. Yet for a brief window, they provide a reliable guide to food. The seal's success lies in exploiting this window, acting quickly and decisively before the trail vanishes completely. Timing becomes as important as sensitivity, reinforcing the need for alertness and efficient decision-making. In ecological terms, this silent superpower influences how prey species behave and distribute themselves. Fish that are frequently hunted by seals may adopt schooling patterns or movement strategies that minimize wake persistence, reducing the likelihood of being tracked. This arms race drives subtle changes in swimming behavior and habitat use, illustrating how sensory adaptations can shape community dynamics over evolutionary timescales. The presence of a predator that hunts by wake rather than sight or sound alters the rules of engagement beneath the surface. Despite its effectiveness, whisker-based tracking remains largely invisible to human observers, overshadowed by more obvious displays of predation. There is no dramatic chase, no sudden explosion of movement, only a seal gliding quietly through water, adjusting course as though guided by intuition. Yet beneath this calm exterior lies a complex sensory process, translating fluid physics into actionable information. The silence of the hunt is not emptiness, but concentration, a focus on signals too subtle to be perceived by most other animals. Understanding this ability reframes how we view intelligence and adaptation in marine mammals. The seal does not rely on large brains or complex vocal communication to achieve success, but on a finely tuned interface with its environment that turns water itself into a source of information. This approach underscores the diversity of solutions evolution produces, each tailored to specific challenges and opportunities. Intelligence here is embodied, expressed through anatomy and behavior rather than abstract problem-solving. As seals continue to move through cold, dim waters, their whiskers sweep the unseen, reading the history of motion written into the sea. Each bend and vibration carries meaning, guiding the animal toward nourishment and safety in a world where sight often fails. This silent radar does not announce itself, does not demand attention, yet it underpins the seal's role as an efficient predator and resilient inhabitant of some of the planet's most challenging marine environments. In following trails left behind by others, seals reveal that the ocean remembers, if only briefly, and that survival belongs to those who know how to listen to what water has to say. The seafloor beneath Arctic and subarctic waters is not the barren plain it can appear to be from above, but a layered archive of life, pressure, and motion, where soft sediments conceal entire communities of organisms just beneath the surface. Light rarely penetrates far enough to define shape or color clearly, and currents move slowly, reshaping the bottom in increments too subtle to notice moment by moment. In this muted, opaque environment, the walrus moves with a confidence that suggests familiarity not just with space, but with texture, density, and hidden form. It does not skim the bottom in search of visible targets, nor does it dig randomly in hope of chance discovery. Instead, it reads the seafloor directly, translating touch into knowledge with a sensory system so precise that buried prey becomes as legible as raised letters beneath a fingertip. A walrus descending toward the bottom does not accelerate or maneuver with elegance, but with mass and inevitability. Its body, heavy with blubber and muscle, settles onto the sediment in a controlled contact that stirs clouds of silt and organic debris. Where a faster or more agile predator might avoid disturbing the environment, the walrus embraces disruption, reshaping the substrate as part of its feeding strategy. The animal's presence alone alters water flow at the boundary between sediment and sea, loosening particles and exposing microcurrents that carry chemical and mechanical cues upward. This disturbance is not collateral damage, but a necessary prelude, preparing the ground for a feeding process that relies on access rather than speed. At the center of this process are the walrus's vibrissae, hundreds of thick, stiff whiskers arranged in dense clusters across the muzzle. These are not delicate filaments, but robust sensory rods, each embedded in a follicle packed with nerve endings capable of detecting fine variations in pressure and texture. When the walrus lowers its head and presses its muzzle against the seafloor, the whiskers splay outward, forming a broad sensory field that sweeps across the sediment. The animal moves slowly, methodically, allowing the vibrissae to probe the surface and shallow subsurface for irregularities that signal the presence of buried prey. Clams, the walrus's primary food source, live just beneath the sediment, protected by shells and the obscuring properties of mud and sand. They do not advertise their presence through movement or sound, and their camouflage is complete to any predator relying on vision. To the walrus's whiskers, however, a clam is a disruption in the otherwise continuous texture of the sea floor, a firm shape embedded within softer material. As the vibrissae encounter these shapes, they bend and transmit mechanical information upward, allowing the walrus to map the distribution of prey across the bottom with remarkable accuracy. The process resembles reading a page written in relief, where meaning emerges not from sight but from contact. Once a clam is located, the walrus shifts from detection to extraction with a technique that appears almost industrial in its efficiency. The animal positions its mouth directly over the target and seals its lips against the sediment, creating a closed system between mouth and ground. With a sudden contraction of muscles in the oral cavity and throat, the walrus generates powerful suction, drawing water and loosened sediment upward. At the same time, it may expel short jets of water downward through its mouth, fluidizing the surrounding sediment and freeing the clam from its burrow. This combination of blasting and vacuuming dislodges prey with minimal effort, lifting it cleanly from the bottom without the need for digging or manipulation. The clam, once freed, is drawn into the mouth, where the walrus uses its tongue and palate to separate soft tissue from shell. The shell is expelled, often falling back to the seafloor in fragments, while the edible portion is swallowed. This process is repeated again and again as the walrus advances across the bottom, leaving behind a trail of disturbed sediment and empty shells that mark its passage. Over time, these feeding tracks can extend for long distances, reshaping benthic landscapes and influencing the distribution of organisms that depend on stable sediment conditions. The walrus's tusks, often the most visually striking feature of the animal, play only a limited role in feeding, despite common misconceptions. They are used primarily for social interactions, defense, and hauling the body onto ice or land, not for digging or prying clams from the bottom. The true tools of feeding are the whiskers and the oral musculature, systems evolved specifically to interact with soft substrates and hidden prey. This reliance on sensory precision over brute force reflects the ecological niche the walrus occupies, one defined by abundance buried beneath obscurity rather than scarcity exposed at the surface. The energy economics of this feeding strategy are finely balanced. Clams are relatively low in caloric density compared to larger prey, requiring the walrus to consume large quantities to meet its metabolic needs. The efficiency of suction feeding allows the animal to process many prey items in rapid succession without excessive expenditure of energy. This efficiency is critical in cold environments, where maintaining body temperature demands constant energy input. The walrus's thick blubber provides insulation, reducing heat loss to the surrounding water, while also serving as an energy reserve that buffers periods of reduced feeding opportunity. Seasonal changes in ice cover and water temperature influence where and how walruses feed. During periods when ice retreats, walruses may be forced to travel farther to reach suitable feeding grounds, increasing the energetic cost of foraging. Their ability to exploit benthic prey efficiently becomes even more important under these conditions, as extended travel leaves less time and energy for feeding itself. In this context, the vibrissae serve not only as sensory organs, but as tools of resilience, enabling walruses to adapt to shifting environmental constraints without abandoning their specialized diet. The ecological impact of walrus feeding extends beyond individual survival. By disturbing sediments and redistributing organic material, walruses act as ecosystem engineers, influencing nutrient cycling and benthic community structure. Their feeding activities can increase oxygen penetration into the sediment, altering microbial processes and affecting the availability of nutrients for other organisms. Shell fragments left behind create new microhabitats, providing surfaces for colonization by algae and invertebrates. In this way, the walrus's role as a predator is intertwined with its role as a modifier of habitat, shaping the seafloor in subtle but significant ways. Young walruses learn these feeding techniques gradually, refining their use of whiskers and suction through repeated practice. Juveniles may initially struggle to locate prey efficiently, sweeping the seafloor with less precision and expending more energy per successful extraction. Over time, experience sharpens their sensory discrimination, allowing them to distinguish between true prey and false signals such as stones or debris. This learning process highlights the importance of neural development and behavioral plasticity in mastering a feeding strategy that relies on fine-scale perception rather than instinct alone. The image of the walrus as a living dredge machine captures the physicality of this behavior but risks obscuring its sensory sophistication. The animal does not bulldoze blindly through the seafloor, but targets its effort with remarkable accuracy, often guided by tactile information that transforms sediment into a readable surface. Each movement of the muzzle is informed by feedback from hundreds of vibrissae, working in concert to build a detailed representation of what lies beneath. The walrus's slow pace is not a limitation, but a feature, allowing time for information to accumulate and decisions to be made with confidence. In the dim, cold waters where walruses feed, sound travels unpredictably, and vision offers little advantage, making touch the most reliable sense for interacting with the environment. The vibrissae extend the walrus's reach beyond the immediate surface, detecting prey before physical contact is made. This extension of perception blurs the boundary between animal and environment, as the walrus becomes attuned to the seafloor in a way that few other large mammals can match. The bottom is not an obstacle but an interface, a medium through which information flows continuously into the animal's nervous system. As the walrus continues its steady advance across the benthic plain, the scene is one of quiet transformation rather than dramatic action. Sediment lifts and settles, shells tumble and come to rest, and the animal moves on, leaving behind a subtly altered landscape. There is no chase, no sudden strike, only the persistent application of a feeding strategy honed by evolution to exploit a resource hidden from most competitors. The effectiveness of this strategy lies in its invisibility, operating beneath the threshold of spectacle, yet sustaining one of the most iconic inhabitants of polar seas. Understanding the walrus as a seafloor vacuum bulldozer reveals a broader truth about life in extreme environments. Survival often depends not on dominance or speed, but on the ability to extract value from places others cannot access. The walrus thrives by turning the seafloor into a readable surface and buried prey into accessible energy, using sensory tools that convert touch into knowledge. In doing so, it demonstrates how adaptation can transform constraint into opportunity, allowing an animal of immense size to subsist on organisms measured in small increments of flesh and shell. In the end, the walrus's feeding behavior is a reminder that the ocean's most powerful processes often occur out of sight, in slow, methodical interactions between organism and environment. The living dredge machine does not roar or flash, but moves with deliberate purpose, reshaping the bottom as it feeds and leaving behind a record written in disturbed sediment and scattered shells. It is a form of engineering executed through biology, where whiskers replace instruments and suction replaces steel, achieving with flesh and nerve what machines can only approximate. In the shallow coastal waters, where light still reaches the bottom and tides breathe life back and forth across sandy flats, the seagrass meadow spreads out like a submerged prairie, quiet, productive, and deceptively fragile. From above, it appears uniform, a green carpet wavering gently with the movement of water. But within this meadow lies a living system built on slow growth, delicate balance, and constant negotiation between consumption and renewal. It is here, moving with unhurried purpose, that the dugong enters the frame, not as a transient visitor, but as a shaping force whose presence quietly rewrites the structure and future of the landscape beneath the surface. The dugong does not arrive with speed or spectacle. Its large, rounded body glides low over the bottom, propelled by slow, powerful strokes of its tail, disturbing the water only slightly as it passes. Unlike predators that cut through the environment in pursuit of prey, the dugong moves as though it belongs to the seafloor itself, its posture and trajectory aligned with the contours of the meadow. Its downturned snout, muscular and flexible, hovers just above the sediment, already reading the texture and density of the grass below. This is not random grazing, nor is it passive consumption. The dugong's movement reflects familiarity, an understanding of where growth is richest and where previous feeding has already reshaped the meadow. Seagrass is not simply underwater vegetation, it is one of the most productive ecosystems on Earth, rivaling tropical rainforests in its ability to capture carbon, stabilize sediment, and support biodiversity. Its roots anchor the seafloor, preventing erosion, while its blades slow water flow, trapping nutrients and organic matter that feed countless invertebrates and fish. For the dugong, seagrass is both sustenance and setting, a resource that must be managed rather than exhausted if survival is to continue across generations. Evolution has shaped the dugong not as a consumer that strips the meadow bare, but as a grazer whose feeding patterns stimulate renewal. When a dugong feeds, it uses its robust lips and bristled snout to uproot entire plants, including roots and rhizomes, pulling them free from the sediment with controlled force. This action leaves behind narrow feeding trails, pale scars where grass has been removed and sediment briefly exposed. To an untrained eye, these trails might appear destructive, evidence of damage inflicted on a vulnerable habitat. In reality, they function much like grazing paths in terrestrial grasslands, resetting growth and triggering a cascade of regenerative responses within the meadow. Seagrass responds to grazing by redirecting energy into new shoots, producing younger, more nutritious blades that grow faster than older, denser stands. These fresh shoots are higher in nitrogen content and more digestible, benefiting not only the dugong, but also other herbivores and detritivores that feed on the meadow. By selectively feeding in patches and moving on rather than remaining in one place, dugongs create a mosaic of growth stages across the landscape, increasing overall productivity and resilience. The meadow becomes structurally diverse, with areas of regrowth interspersed among mature stands, supporting a wider range of species than a uniform field ever could. The dugong's influence extends beyond the plants themselves into the sediment below. Uprooting seagrass loosens compacted sand and mud, increasing oxygen penetration and altering microbial activity within the seabed. This shift affects nutrient cycling, as bacteria break down organic matter more efficiently, releasing nutrients back into the water column where they can be reused by plants. The dugong, in feeding, accelerates processes that would otherwise occur slowly, acting as a catalyst that keeps energy moving through the system rather than locked away in aging plant material. This relationship between dugong and meadow is not accidental, but the result of co-evolution over immense timescales. Dugongs have specialized digestive systems adapted to process fibrous plant material, relying on microbial fermentation to extract nutrients from cellulose. Their slow metabolism and low activity levels match the energy yield of their diet, allowing them to survive on a food source that would be insufficient for faster, more demanding animals. At the same time, seagrass species in regions where dugongs are present have evolved to tolerate and even depend on grazing, demonstrating rapid regrowth and resistance to uprooting that would devastate less adapted plants. Movement through the meadow follows a pattern shaped by memory and environmental feedback rather than impulse. Dugongs often return to feeding grounds they have visited before, timing their visits to coincide with optimal regrowth stages. This behavior suggests an awareness of the meadow as a dynamic system rather than a static resource, where overuse would diminish future returns. The dugong's slow pace, often interpreted as lethargy, is better understood as restraint, a strategy that balances consumption with conservation. The presence of a feeding dugong also alters how other animals use the meadow. Fish and invertebrates are drawn to freshly grazed areas, where exposed sediment and new growth create feeding opportunities. Predators follow, not to hunt the dugong, which has few natural enemies, but to exploit the increased activity around its feeding trails. In this way, the dugong acts as a keystone modifier, initiating a chain reaction that increases local biodiversity. Its feeding scars become hubs of interaction, small disturbances that ripple outward through the ecosystem. Thermoregulation plays a subtle role in this lifestyle. Dugongs inhabit warm, shallow waters, where maintaining body temperature requires less energy than in colder environments, allowing them to allocate more resources toward digestion and slow movement. Their thick skin and layer of blubber provide insulation, but also buoyancy, enabling them to hover just above the bottom with minimal effort. This buoyancy control is critical for precise grazing, allowing the dugong to apply downward force when uprooting plants without sinking fully into the sediment. Migration patterns further reinforce the dugong's role as a landscape shaper. Seasonal movements between feeding grounds track changes in seagrass availability driven by temperature, storms, and freshwater input. Rather than exhausting one meadow, dugongs distribute their grazing pressure across multiple sites, giving each area time to recover. This mobility ensures long-term sustainability of their food source, while linking distant meadows into a connected ecological network. Nutrients consumed in one location may be excreted in another, effectively transporting fertility across the coastal zone. Despite their size and influence, dugongs exert their power quietly. There is no dramatic confrontation, no visible struggle between animal and environment. The transformation occurs slowly, almost imperceptibly, as feeding trails fade and regrowth fills in behind them. This subtlety is precisely what makes the dugong's role easy to overlook and easy to disrupt. When dugongs disappear from a region, seagrass meadows often change character, becoming denser but less productive, more prone to disease, and less capable of supporting diverse communities. The absence of grazing allows old growth to dominate, reducing nutrient turnover and weakening the system's resilience to environmental stress. Human activity has made this balance increasingly fragile. Coastal development, boat traffic, and pollution damage seagrass directly, while accidental entanglement and habitat fragmentation threaten dugong populations. The loss of either partner destabilizes the entire system, illustrating how tightly linked their fates have become. The dugong is not merely dependent on the meadow depends on the dugong to remain healthy and dynamic. This mutual reliance challenges simplistic views of herbivores as passive consumers and highlights the active role they play in shaping ecosystems. From a broader perspective, the dugong embodies a form of power rooted in influence rather than dominance. It does not control the meadow through force, but through participation, engaging with the environment in a way that promotes long-term stability. Its feeding behavior reflects a balance between need and restraint, where survival is achieved not by taking everything available, but by taking just enough to encourage renewal. This approach contrasts sharply with extractive strategies that lead to collapse, offering a model of coexistence grounded in feedback and adaptation. As the dugong moves on, leaving behind a patchwork of grazed and ungrazed seagrass, the meadow begins its quiet work of recovery. New shoots emerge, sediment settles, and microbial processes continue unseen beneath the surface. The animal's passage is marked not by destruction but by change, a temporary disruption that fuels growth rather than halting it. Over time, these changes accumulate, shaping the meadow's structure and productivity in ways that benefit countless organisms beyond the dugong itself. To view the dugong merely as a gentle grazer is to miss the scale of its impact. It is an ecosystem engineer operating at a pace that mirrors the rhythms of the environment it inhabits, aligning its life history with the slow cycles of plant growth and nutrient exchange. Its power lies in consistency rather than intensity, in the repeated, deliberate actions that gradually transform space into habitat and habitat into sustenance. In the quiet shallows where seagrass bends and sunlight filters through water, the dugong continues its work, unseen by most and understood by few. It farms not with fences or tools, but with movement and appetite, cultivating a living landscape through presence alone. The meadow responds, growing back richer and more diverse, sustained by a relationship forged over evolutionary time. This is not a story of consumption, but of influence, where survival is secured not by conquest, but by shaping the conditions that allow life to persist. The coastal boundary where land dissolves into sea is a place of constant negotiation, shaped by tides, storms, and the quiet pressure of organisms competing for space and energy. In these nearshore waters, kelp forests rise from rocky bottoms like submerged cities, their long fronds stretching toward light while anchoring themselves against relentless surge. These forests appear stable and self-sustaining, but their existence depends on a fragile balance maintained not by plants alone, but by a predator whose influence far exceeds its physical size. The sea otter moves through this environment with an ease that conceals its role as a regulator, a species whose daily choices determine whether the coastline remains lush and productive or collapses into ecological emptiness. At the surface, a sea otter seems almost casual, floating on its back, grooming its dense fur, or drifting with the swell as though unconcerned by the complexity beneath. This impression is misleading. Every movement, every dive, and every feeding decision contributes to a network of interactions that shape the structure of the ecosystem. The otter's body is not built for speed or size dominance, but for dexterity, precision, and endurance in cold water. Unlike most marine mammals, Sea otters lack a thick layer of blubber, relying instead on the densest fur of any mammal to trap air and insulate against heat loss. This dependence on fur makes grooming a survival behavior, but it also anchors the otter's lifestyle close to shore, where food resources and shelter allow frequent resurfacing. Diving beneath the surface, the otter becomes a focused forager, scanning the sea floor with sensitive forepaws that can distinguish texture and shape with remarkable accuracy. Its vision and whiskers assist, but it is touch that dominates, allowing the otter to locate prey hidden among rocks, crevices, and kelp holdfasts. Sea urchins, abalone, crabs, and clams form the core of its diet, organisms protected not by speed but by armor, spines, or shells. For most predators, these defenses would be prohibitive, but the otter counters them with a combination of anatomy and behavior that sets it apart from nearly all other marine mammals. Tool use is central to this strategy. When an otter surfaces with a hard-shelled prey item, it often retrieves a rock from the seafloor or from a pouch of loose skin beneath its forearm, a natural pocket evolved specifically for carrying objects. Floating on its back, the otter positions the rock on its chest and repeatedly strikes the prey against it with controlled force, cracking shells that would otherwise be impenetrable. This behavior is not random or instinctive in the simplistic sense. Otters show preference for rocks of certain sizes and shapes, and individuals refine their technique over time. Young otters learn by observation and practice, initially clumsy, gradually improving efficiency as experience accumulates. The act of cracking a shell is only the visible expression of a deeper behavioral adaptation. Selective foraging. Otters do not consume prey indiscriminately. They assess size, hardness, and nutritional value, often choosing individuals that maximize energy return relative to effort. This selectivity influences prey populations directly, as certain size classes or species are removed more frequently than others. Over time, this pressure shapes the composition of benthic communities, altering growth rates, reproductive strategies, and even behavior of prey species, attempting to avoid predation. Among all prey, sea urchins occupy a particularly critical position in this story. Urchins are efficient grazers, capable of stripping kelp holdfasts and consuming young shoots at a pace that can outstrip regrowth. In the absence of predators, urchin populations can explode, transforming complex kelp forests into barren seascapes dominated by spines and rock. These so-called urchin barrens support far less biodiversity, as the loss of kelp removes shelter, food, and nursery habitat for countless species. The difference between a thriving kelp forest and a biological desert can hinge on the presence or absence of a single predator. Sea otters fill this role with precision. By preying heavily on urchins, they keep grazing pressure in check, allowing kelp to establish and persist. This is not a simple reduction in numbers, but a restructuring of behavior. In regions with otters, urchins often retreat into crevices and reduce their feeding activity, becoming smaller and less aggressive grazers. Kelp responds quickly, expanding its canopy and increasing primary production. This growth creates habitat for fish, invertebrates, and other organisms, cascading upward through the food web. The otter's influence does not stop at kelp. Dense kelp forests dampen wave energy, reducing coastal erosion and stabilizing sediments. They capture carbon, contributing to climate regulation, and provide refuge for commercially important species. By maintaining these forests, otters indirectly support fisheries, shoreline integrity, and nutrient cycling. This chain of effects illustrates a trophic cascade, where changes at one level propagate through the system, amplifying the impact of individual behaviors into landscape-scale outcomes. What makes the sea otter's role especially striking is that it does not rely on sheer abundance or dominance. Otter populations are relatively small compared to the biomass of kelp they protect. Their power lies in targeting a keystone prey species and altering its ecological function. This targeted influence represents a form of ecological leverage, where precise intervention yields disproportionate results. The otter does not need to control every species. It needs only to control the right one. The spatial aspect of this influence is equally important. Sea otters have home ranges that they patrol regularly, diving repeatedly in familiar areas and revisiting productive patches. Their feeding patterns create mosaics of pressure and relief across the seafloor, preventing any single prey population from overwhelming the system. These patterns are dynamic, shifting with seasons, reproductive cycles, and individual preferences. Over time, the coastline becomes a patchwork shaped by otter activity, with kelp forests flourishing where otters are active and declining where they are absent. Migration and movement patterns reinforce this role. Otters do not undertake long oceanic migrations like some marine mammals, but they do disperse along coastlines, recolonizing areas where populations have been reduced or eliminated. Historical records reveal that when otters return to regions from which they were extirpated, kelp forests often recover dramatically. These recoveries are not gradual or subtle. They can transform entire coastal ecosystems within years, underscoring how quickly ecological balance can be restored when a keystone species resumes its role. Thermoregulation adds another layer to this story. Maintaining body heat in cold water requires constant energy intake, driving the otter to consume a large proportion of its body weight each day. This high metabolic demand ensures that otters forage almost continuously, reinforcing their regulatory effect on prey populations. What might seem like vulnerability becomes a driver of ecological stability, as the otter's need to eat translates directly into sustained predation pressure on species that would otherwise dominate. The relationship between otters and kelp forests also highlights the interconnectedness of marine and terrestrial systems. Kelp forests influence nutrient availability and water clarity, which in turn affect coastal productivity. They provide shelter for fish that later move into open waters, linking nearshore habitats to broader oceanic systems. By safeguarding kelp, otters indirectly support processes that extend far beyond their immediate surroundings, making their role both local and global in consequence. Human history has repeatedly demonstrated how fragile this balance can be. The removal of sea otters through hunting led to widespread kelp forest collapse in many regions, followed by declines in biodiversity and changes in coastal structure. These shifts were not anticipated at the time, as the otter was viewed simply as a resource rather than a regulator. Only later did the true extent of its influence become clear, revealing how the loss of a single species can unravel systems built over millennia. Tool use, often highlighted as a marker of intelligence, takes on deeper significance in this context. The otter's ability to manipulate objects allows it to access prey that would otherwise be unavailable, enabling its role as a keystone predator. This behavior is not an isolated curiosity, but a functional adaptation with ecosystem-wide implications. By cracking shells, the otter opens pathways of energy flow that shape the entire food web. Seen through this lens, the sea otter is not merely a charismatic animal performing clever tricks, but a gatekeeper whose actions determine the fate of habitats far larger than itself. Its superpower is not strength or speed, but influence, the capacity to change the map of life along the coast through everyday choices repeated across generations. Each dive, each cracked shell, contributes to a pattern that sustains forests, stabilizes shores, and supports countless forms of life. As the otter surfaces once more, floating amid kelp fronds that sway gently with the tide, the scene feels tranquil, almost static. Yet beneath this calm lies a dynamic equilibrium maintained through constant interaction. The otter's presence holds the system together, not through dominance, but through participation, reminding us that ecosystems often depend on unlikely guardians. In understanding the sea otter's role, we glimpse a broader truth about nature, that power is often subtle, expressed not through force, but through the ability to shape relationships, guiding energy and life into forms that endure. Along rocky reefs and coral outcrops, where light fractures into shifting patterns and shadows never fully settle, the octopus exists as something less like an animal and more like a process unfolding in real time. It does not simply occupy space within the environment. It continuously negotiates its appearance, posture, and behavior to match the physics and biology around it. To observe an octopus is to watch matter deciding how to be seen, or whether to be seen at all. What looks like camouflage is not a single trick or reflex, but a layered system of perception and response so complex that it challenges how intelligence itself is defined in the natural world. At rest, an octopus may appear indistinguishable from the rock it clings to, its skin mottled and roughened, arms folded into irregular angles that mirror the fractured geometry of the reef. This resemblance is not superficial. The animal's skin contains multiple types of specialized cells that operate together to manipulate light, texture, and even perceived depth. Chromatophores expand and contract to reveal pigments of brown, red, yellow, or black, while iridophores and leucophores beneath them reflect and scatter ambient light, matching brightness and polarization rather than color alone. The result is not a flat disguise, but a dynamic surface that responds to viewing angle, water clarity, and sun position, allowing the octopus to blend into environments that change by the minute. Texture is as important as color, and here the octopus reveals another layer of control. Muscular structures in the skin, called papillae, can be raised or flattened at will, transforming smooth flesh into spiky ridges, knobby protrusions, or rippled surfaces that mimic coral, algae, or rubble. These changes occur in fractions of a second, synchronized with color shifts to create a convincing three-dimensional illusion. The octopus is not copying a specific object so much as matching the statistical properties of its surroundings, replicating the general roughness, contrast, and irregularity that define the background. In doing so, it exploits the limitations of visual perception in predators, which rely on pattern recognition rather than detailed analysis. Posture and motion complete the illusion. An octopus does not move like an octopus when it wants to remain hidden. Instead, it adopts movement patterns that resemble drifting algae, rolling stones, or the slow sway of kelp in current. Arms extend and retract in asynchronous waves, breaking the outline of the body and eliminating recognizable symmetry. Even when traveling across open ground, the octopus may choose to crawl rather than swim, hugging the substrate and reshaping itself continuously to avoid presenting a stable target. Motion, often the giveaway for camouflage, becomes another variable under control, adjusted to match environmental rhythms. This mastery of appearance is underpinned by a nervous system unlike that of any other large invertebrate. While the octopus possesses a central brain, more than half of its neurons are distributed throughout its arms, embedded in a network that allows each limb to process sensory input and generate movement semi-independently. An arm can explore, taste, and manipulate objects without direct instruction from the central brain, responding locally to stimuli while still contributing to coordinated behavior. This decentralization allows the octopus to manage its complex body efficiently, freeing the brain to focus on higher-level decisions rather than micromanaging every motion. Each arm is lined with suckers that function as both grasping tools and sensory organs. These suckers can detect chemical cues, texture, and pressure, effectively allowing the octopus to taste and feel the world through touch. When an arm encounters something of interest, it does not wait passively for commands, but engages immediately, probing, pulling, or adjusting grip as needed. The central brain monitors these interactions, integrating information across arms and adjusting overall strategy, but much of the detailed work happens locally. This arrangement creates a form of parallel processing, where multiple streams of information are handled simultaneously, enabling rapid and flexible responses to complex environments. The result is behavior that appears improvisational, even theatrical, as though the octopus is staging a performance for its audience. In reality, it is executing a continuous series of context-dependent decisions, balancing the need to remain hidden against the need to move, hunt, or escape. When threatened, the octopus may escalate its deception, transforming not just into background, but into another organism entirely. Certain species can mimic the appearance and behavior of venomous animals, such as sea snakes or lionfish, altering arm posture and swimming style to present a credible threat rather than concealment. This mimicry is not perfect, but it is often sufficient to deter predators long enough for escape. Hunting reveals yet another facet of this living special effects system. An octopus stalking prey does not rely on speed alone, but on surprise and precision. It may approach a crab or fish while camouflaged, closing distance slowly until a sudden burst of motion captures the prey before it can react. Arms shoot forward, suckers adhering instantly, while the beak delivers a bite that injects venom to immobilize the victim. Throughout this process, the octopus adjusts color and texture to match the immediate surroundings, minimizing detection even as it strikes. The environment itself becomes part of the hunt, a stage set manipulated by the predator. The intelligence behind these behaviors is not abstract in the way human intelligence often is, but embodied, expressed through the interaction of nervous system, body, and environment. Learning occurs through exploration and experience, as octopuses remember successful strategies and adapt them to new situations. They can solve problems, navigate mazes, and even manipulate objects to achieve goals, yet their cognition remains deeply tied to physical engagement with the world. Each arm gathers data, each movement tests a hypothesis, and the skin broadcasts the result as a visible outcome. This embodied intelligence carries costs as well as benefits. Maintaining such a complex nervous system and responsive skin requires significant energy, contributing to the octopus's relatively short lifespan. Many species live only a few years, compressing a remarkable range of behaviors into a brief existence. This brevity adds urgency to their interactions with the environment, as each moment must balance survival, growth, and reproduction within a limited time frame. The octopus's ability to adapt rapidly and creatively may be a response to this constraint, favoring flexibility over longevity. Reproduction marks a dramatic shift in behavior, as females dedicate themselves entirely to guarding and aerating their eggs, often refusing food and fading physically as their energy reserves are consumed. During this period, the same skin that once shifted constantly becomes subdued, and the same arms that explored the world tirelessly now focus on a single task. This transition underscores the trade-offs inherent in the octopus's life strategy, where intense investment in intelligence and adaptability culminates in a single reproductive event. Ecologically, octopuses play multiple roles, both as predators shaping populations of crustaceans and small fish, and as prey for larger animals capable of seeing through or overwhelming their defenses. Their camouflage influences predator behavior, selecting for those able to detect subtle inconsistencies in pattern or motion. In turn, octopuses refine their disguises, driving an evolutionary dialogue played out through perception and deception rather than force. The reef becomes a testing ground for sensory systems, with success measured not in strength, but in the ability to remain unread. The alien quality often attributed to octopus intelligence arises from this combination of distributed cognition, radical body flexibility, and visual manipulation. There is no single face, no stable form, no clear separation between thinking and acting. Decision-making flows through the body, expressed as changes in color, texture, and movement that blur the line between internal state and external appearance. The octopus does not wear camouflage. It becomes it, merging perception and presentation into a single, continuous process. From a human perspective, this challenges familiar assumptions about how minds operate. Intelligence is often associated with centralized control and symbolic reasoning, yet the octopus demonstrates that complex problem-solving and adaptive behavior can emerge from decentralized systems deeply embedded in physical interaction. Each arm contributes its own perspective, each patch of skin responds locally to light and touch, and the whole organism coordinates these responses into coherent action without a single commanding voice. In the shifting light of the reef, an octopus may vanish entirely, leaving behind only the impression that something was there moments before. This disappearance is not magic, but the result of biological systems operating at the edge of what perception can resolve. The living special effects studio folds itself away, sets dismantled, lights dimmed, performers gone. What remains is the environment, unchanged in appearance, yet subtly altered by the presence of an intelligence that moved through it unseen. To understand the octopus is to accept that intelligence does not require familiarity, and that mastery of an environment can take forms that defy categorization. It is a reminder that evolution explores possibilities beyond linear progression, producing minds that think with skin, arms, and motion as much as with neurons. In watching an octopus reshape itself to match the world, we glimpse a mode of existence where adaptation is continuous and identity is fluid, an alien intelligence not visiting our planet, but having evolved quietly beneath the surface all along. In the shallow continental shelves and sloping reefs where light still penetrates, but vision can no longer be trusted, the cuttlefish moves through water as if wrapped in a living interface, its body not merely occupying space, but actively negotiating how that space perceives it. To witness a cuttlefish in motion is to observe an animal that does not rely on a single form of deception, but on a layered system of visual manipulation so advanced that it often appears unreal, as though the rules of biology have been bent for dramatic effect. Yet every flicker of color, every ripple across its skin, and every shift in posture is grounded in physical structures and neural control refined by evolution for one purpose: absolute dominance over perception. At first glance, a cuttlefish resting on the seafloor may appear unremarkable, its oval body blending seamlessly with sand or rubble, arms tucked close, outlines softened into anonymity. This stillness is not passivity but readiness, the baseline state of a system capable of instant transformation. Beneath the surface of the skin lies a complex hierarchy of specialized cells, each contributing a different layer of visual information. Chromatophores sit at the top, elastic sacs of pigment controlled directly by muscles rather than hormones, allowing for rapid expansion and contraction that changes visible color in fractions of a second. These pigments alone would already place cuttlefish among the fastest color changes in the animal kingdom, but they are only the first layer. Beneath the chromatophores lie iridophores, cells that do not contain pigment at all, but instead reflect light through microscopic plate structures that interfere with incoming wavelengths. These reflections produce shimmering blues, greens, and silvers that shift depending on viewing angle and ambient light conditions. Unlike pigment-based color, which absorbs light, iridescence manipulates it, adding brightness and directional flash to the cuttlefish's appearance. Below these sit leucophores, broadband reflectors that scatter light evenly, matching the overall brightness of the surrounding environment. Together, these layers allow the cuttlefish not only to change color, but to control contrast, luminosity, and reflectivity independently, producing an illusion that responds dynamically to the physics of light itself. Texture completes the deception. Muscular papillae embedded in the skin can be raised or flattened at will, transforming a smooth body into a rough, knobby surface that mimics gravel, coral fragments, or algae-encrusted rock. These changes are not slow adjustments, but rapid sculptural shifts, synchronized with color and pattern changes to eliminate telltale outlines. A cuttlefish can move from flat sand mimicry to jagged reef camouflage in less time than it takes a predator to focus, reshaping not just its appearance, but its perceived physical structure. This system operates under direct neural control, bypassing slower chemical signaling pathways and allowing immediate response to environmental cues. The cuttlefish does not cycle through preset disguises, but assembles patterns in real time, adjusting based on background complexity, light angle, and the likely sensory capabilities of whatever is watching. This ability reveals a deep integration between perception and expression, where seeing and becoming are part of the same process. The cuttlefish's brain continuously evaluates the scene, selecting which elements of the visual system to activate and to what degree in order to produce the most convincing illusion possible. When hunting begins, this visual mastery takes on an even more unsettling dimension. Rather than relying on pursuit, the cuttlefish often approaches prey slowly, body hovering just above the substrate, patterns shifting subtly to remain non-threatening. At the critical moment, it deploys a display that seems designed to overwhelm the prey's sensory processing. Waves of contrasting light and dark bands ripple across the body, moving in coordinated pulses that draw the prey's attention and disrupt its ability to assess distance or direction. These so-called passing cloud displays are not random flashes, but structured visual signals that exploit the way many fish process motion and contrast, effectively holding them in place through sensory overload. The prey, caught in this cascade of shifting patterns, often fails to register the cuttlefish's true position or intent. While the visual system of the prey attempts to interpret the moving bands, the cuttlefish closes the final distance. In a sudden release of speed, two specialized feeding tentacles shoot forward, extending far beyond the body length to seize the target with adhesive pads. The strike is precise and efficient, ending the interaction before the prey can react. The hypnotic display ceases immediately, replaced by a subdued pattern as the cuttlefish consumes its meal. What looked like theatrical excess moments earlier reveals itself as a finely tuned predatory tool. Underlying this ability is another extraordinary adaptation: polarization vision. Unlike humans, who perceive only color and brightness, cuttlefish can detect the orientation of light waves, a property known as polarization. Many marine surfaces, including fish scales and the water itself, reflect polarized light in specific ways. To a cuttlefish, this adds an additional layer of information, revealing contrasts and patterns invisible to most other animals. Polarization. Sensitivity allows cuttlefish to detect prey even when color contrast is minimal, to identify reflective surfaces, and possibly to communicate with other cuttlefish using signals hidden from predators that lack this sensory channel. This sensory advantage feeds directly into their camouflage and display strategies. Patterns that appear subtle or uniform to human eyes may stand out starkly in polarized light, and cuttlefish appear capable of exploiting this difference, tailoring displays to be conspicuous or concealed depending on the viewer. In this way, the cuttlefish operates within multiple perceptual worlds simultaneously, crafting appearances that mean different things to different observers. A predator might see an unremarkable patch of sand, while prey perceives a moving, disorienting signal that disrupts its escape response. The intelligence required to manage this complexity is distributed throughout the nervous system, with rapid communication between sensory input and motor output. While the cuttlefish has a centralized brain, much of its control over skin patterning occurs through localized neural circuits that allow sections of the body to respond independently. This decentralization enables parallel processing, where multiple visual elements can be adjusted at once without overwhelming a single control center. The result is a fluid, adaptive display that responds instantly to changes in the environment. Beyond hunting, these visual systems play roles in social interaction and threat deterrence. When confronted by a potential predator, a cuttlefish may shift from camouflage to bold, high-contrast patterns that signal alertness and readiness. Dark eye bars, sudden flashes, and exaggerated textures can make the animal appear larger or more dangerous than it is. These displays are not bluff in the traditional sense, but calculated manipulations of perception, designed to create uncertainty and hesitation. In an environment where milliseconds matter, hesitation can be the difference between survival and capture. The energy cost of maintaining such a responsive system is significant. Rapid muscle contractions in chromatophores and papillae, constant neural activity, and high visual processing demand fuel, contributing to the cuttlefish's relatively short lifespan. Like many cephalopods, cuttlefish grow quickly, reproduce once, and die young, compressing a lifetime of complex behavior into a brief existence. This life history strategy favors adaptability and speed over longevity, allowing cuttlefish to exploit transient opportunities in dynamic environments. Ecologically, cuttlefish occupy a critical role as mid-level predators, regulating populations of crustaceans and small fish while serving as prey for larger animals capable of seeing through or overpowering their defenses. Their camouflage and displays influence predator behavior, selecting for species that rely on senses other than vision or that can process complex visual information. In turn, cuttlefish refine their techniques, escalating an evolutionary dialogue centered on perception rather than force. What makes the cuttlefish especially striking is how technological its solutions appear, as though engineered rather than evolved. Layered optical systems, distributed control networks, and sensory channels beyond human experience combine to produce effects that resemble digital screens, special effects, or optical illusions. Yet these systems arise entirely from biological materials operating within the constraints of muscle, nerve, and light. There is no abstraction, no separation between hardware and software. The The cuttlefish's body is both interface and processor. This integration blurs the boundary between appearance and action. A change in color is not cosmetic, but communicative. A shift in texture, not decorative, but defensive. The cuttlefish's skin is a language written in light and shadow, read differently by every observer. It is a language that can calm, confuse, intimidate, or hypnotize, depending on context. Mastery of this language allows the cuttlefish to survive in an environment where speed and strength alone would not suffice. To describe the cuttlefish as a mood ring understates the precision of its control. Yet the metaphor captures something essential about its relationship with the world. Its skin reflects not emotion, but intention, strategy, and assessment, broadcasting information shaped by continuous evaluation of risk and opportunity. Every ripple of pattern is a decision made visible, a thought translated into form. In the shifting light of the seafloor, where predators and prey are locked in constant negotiation, the cuttlefish stands as a reminder that evolution does not always favor brute solutions. Sometimes, survival belongs to those who can rewrite perception itself, turning the act of being seen into a weapon. The mood ring assassin does not simply hide or attack. It edits reality for those around it, bending attention, expectation, and response to its advantage. What looks fake is not illusion, but sophistication, a living system so advanced that it exposes the limits of how we imagine intelligence, camouflage, and power in the natural world. In the shallow tropical waters, where coral rubble forms a chaotic mosaic of broken stone and living reef, the mantis shrimp occupies a narrow, fortified world of burrows and crevices that few other animals can safely approach. At first glance, nothing about this environment suggests extreme physics. Water softens impacts, slows motion, and absorbs energy, turning violence into drag and turbulence. Yet within this seemingly forgiving medium lives an animal that has evolved a strike so violent, so precisely timed, that it briefly overrides the rules most creatures are bound by. The mantis shrimp does not merely hit its prey, it momentarily turns water itself into a weapon. The animal's body is compact and armored, its posture low and coiled as it waits near the entrance of its burrow. This is not the stance of an active pursuer, but of a system primed for release, storing energy the way a crossbow stores tension. The mantis shrimp's raptorial appendages, folded tightly beneath its head, are modified limbs that function not as simple claws, but as spring-loaded clubs or spears, depending on the species. In smashers, the terminal segment of the limb is enlarged into a dense, hammer-like structure, composed of highly ordered layers of mineralized material and organic fibers. This club is not brittle despite its hardness. Its internal architecture dissipates stress in spiraling patterns that prevent catastrophic failure under repeated impacts. Before the strike, muscles within the limb contract slowly, loading elastic structures that act like biological springs. These structures, composed of specialized proteins, store energy over a fraction of a second, while the limb remains locked in place by a latch mechanism. This latch is critical, as it allows the animal to bypass the normal speed limits imposed by muscle contraction. Muscles alone cannot move fast enough to produce the velocities observed in a mantis shrimp strike. Instead, they preload the system, and when the latch releases, stored energy is discharged almost instantaneously. What follows is not a swing, but an explosion of motion. The club accelerates forward at a rate that rivals the fastest movements known in the animal kingdom, reaching peak velocity in a time span so short that it challenges conventional measurement. As the club moves, it does not simply push water aside, it outruns the ability of water molecules to flow back into place. Pressure drops precipitously behind the advancing surface of the club, creating a void where liquid can no longer remain stable. In this moment, cavitation occurs, and vapor bubbles form in the low-pressure zone trailing the strike. This phenomenon is familiar to engineers as a destructive force that erodes ship propellers and turbine blades, but here it is harnessed deliberately by living tissue. The first impact happens when the club itself collides with the target, whether that target is a crab shell, a snail, or the armored exoskeleton of another crustacean. The force delivered is sufficient to fracture calcium carbonate structures that would otherwise resist crushing, often killing or stunning prey outright. Yet the mantis shrimp strike does not end there. Almost immediately after the club makes contact and begins to decelerate, the cavitation bubbles collapse. This collapse is not gentle. As surrounding water rushes back to fill the void, the bubbles implode, releasing a secondary shockwave accompanied by a brief flash of light known as sonoluminescence. This second odor, delivered by collapsing bubbles rather than physical contact, propagates through water and into the target, adding to the damage inflicted by the club itself. In some cases, this shockwave alone is sufficient to injure or kill prey, even if the initial blow misses slightly. The mantis shrimp has effectively engineered a two-stage weapon, one that strikes once with solid matter and again with a pressure wave generated by the physics of fluids under extreme acceleration. The prey experiences not a single event, but a rapid sequence of forces that overwhelm structural defenses evolved to withstand far slower, simpler attacks. What makes this even more remarkable is that the mantis shrimp performs this feat repeatedly without injuring itself. The club's internal structure is arranged in a helicoidal pattern, layers twisted in gradual rotation that spread stress across the limb rather than allowing it to concentrate at a single point. Micro cracks that do form are deflected along these layers, preventing them from propagating into catastrophic fractures. This design is so effective that materials scientists study mantis shrimp clubs to inform the development of impact-resistant composites for human use. The animal is not merely surviving its own weapon, it is optimized around it. The burrow from which the mantis shrimp strikes is an extension of this strategy. These burrows are often U-shaped or reinforced with rubble, providing both protection and a controlled environment from which the shrimp can launch attacks. The mantis shrimp positions itself with precision, calculating distance and angle before committing to the strike. Despite the speed involved, accuracy is high, suggesting a sensory system capable of fine depth perception and timing. The animal's complex eyes, capable of detecting polarized light and a wide range of wavelengths, likely contribute to this targeting ability, though the exact neural integration remains an active area of research. Prey species in these habitats are not passive victims. Many possess thick shells, spines, or behaviors designed to deter predators. The mantis shrimp's strike represents an evolutionary escalation in this arms race, a response to defenses that made conventional crushing ineffective. By introducing cavitation into the equation, the mantis shrimp bypasses the need for brute force alone, exploiting a physical phenomenon that prey cannot easily evolve defenses against. Shell thickness becomes less relevant when the surrounding medium itself becomes destructive. This strategy has ecological consequences beyond individual predation events. Mantis shrimp influence the distribution and behavior of shelled invertebrates, shaping community structure on reefs and sandy bottoms. Areas with high mantis shrimp activity often show altered species composition, as vulnerable prey either decline or adopt behaviors that reduce exposure. Burrow placement can affect sediment turnover as the shrimp excavates and reinforces its habitat, subtly modifying local microenvironments. The mantis shrimp is not just a predator, but an agent of change in its ecosystem. Its presence felt through both direct and indirect pathways. Energy expenditure is another critical aspect of this system. Loading the strike requires muscular effort, and repeated strikes demand efficient recovery. The mantis shrimp balances this cost by targeting prey that offers high nutritional return relative to effort. A successful strike can secure a meal that sustains the animal for extended periods, reducing the need for constant hunting. This efficiency is essential in environments where food availability fluctuates and competition is intense. Thermoregulation plays a subtle role as well. In warmer waters, muscle and elastic tissues perform more efficiently, allowing faster loading and release of the strike mechanism. This may partly explain the prevalence of mantis shrimp in tropical and subtropical regions, where environmental conditions favor their extreme biomechanics. Temperature influences not only metabolic rate, but also the material properties of biological tissues, shaping where such a weapon can function optimally. The viral appeal of the mantis shrimp often focuses on the raw numbers associated with its strike, but this emphasis risks missing the deeper story. The punch is not impressive because it is fast or strong in isolation, but because it represents a convergence of biology and physics, rarely seen so clearly in nature. The mantis shrimp does not violate physical laws. It exploits them with precision, operating at the edge of what is possible within a living system. The cavitation bubble is not a byproduct but an integral component of the weapon, a feature that has been incorporated into the animal's hunting strategy through evolutionary refinement. From the perspective of the prey, there is no warning. The strike is too fast to see, too sudden to evade. One moment, the burrow entrance is still. The next, it is the epicenter of a localized catastrophe. Shells shatter, tissues rupture, and shockwaves ripple outward, dissipating harmlessly into the surrounding water once their work is done. The environment absorbs the violence, leaving little trace beyond broken fragments and an empty burrow entrance where the mantis shrimp retreats to consume its meal. In a broader sense, the mantis shrimp challenges assumptions about scale and power in the ocean. It demonstrates that extreme impact does not require massive size, and that small organisms can wield forces that rival or exceed those generated by much larger animals, provided they are engineered correctly. This lesson resonates beyond biology, influencing how engineers think about energy storage, release, and material design. As the mantis shrimp resets its weapon, slowly reloading elastic structures beneath its armored shell, the reef returns to its usual rhythms. Fish pass overhead, currents stir sand and detritus, and the violence of the strike fades into memory. Yet the rules of this environment have been momentarily rewritten, water transformed into a conduit for force rather than a cushion against it. This is the true power of the mantis shrimp's punch, not that it breaks shells, but that it reveals how deeply physics is woven into survival strategies at every scale of life. In the end, the mantis shrimp stands as a reminder that the ocean is not only a place of fluid motion and gentle drift, but also a domain where extreme events can be generated by organisms no larger than a human hand. The biological hammer does not roar or glow for long, but in the instant it strikes, it compresses evolution, physics, and ecology into a single unforgettable moment. In the shallow reefs and coastal shallows where coral heads cast broken shadows and the water is rarely still, the pufferfish drifts through the environment with an almost casual lack of urgency. Its movement is unhurried, even clumsy by the standards of fast predators that patrol these spaces. It does not slice through the water like a tuna or glide with the precision of a shark. Instead, it paddles with small fins, hovering more than swimming, as though speed were a forgotten option rather than a limitation. This apparent vulnerability is not an oversight of evolution, but a calculated trade, one that replaces escape with transformation and rewrites the rules of predation through sudden, overwhelming physical change. Under normal conditions, the pufferfish presents a modest profile. Its body is compact, rounded and soft, lacking the armor, speed or sharp weaponry associated with survival in predator-rich environments. The skin appears smooth or lightly textured, the spines flattened and barely noticeable, folded against the body like unused equipment. In this state, the fish blends into the reef as another slow-moving grazer or curious bystander, its behavior offering no hint of the radical shift it can undergo in moments of extreme threat. Predators watching from a distance may register it as an easy target, an organism that failed to invest in the obvious defenses of speed or aggression. The transformation begins not with movement, but with ingestion. When a predator commits to the attack, the pufferfish reacts instantly by opening its mouth and rapidly drawing in water, sometimes air if near the surface, using powerful muscles to expand a specialized stomach capable of stretching far beyond its resting volume. This stomach is not a typical digestive organ, but a highly elastic chamber reinforced to withstand sudden expansion without tearing. As water floods in, the body inflates outward in all directions, multiplying its apparent size in seconds. What was once a small, manageable prey item becomes a swollen sphere that strains the predator's jaws and alters the physical geometry of the encounter. As the body expands, another system activates in parallel. The pufferfish's spines, which lay flat against the skin when deflated, are anchored to the dermis in such a way that inflation forces them to rise and lock into position. These spines do not grow during inflation, they are revealed by it, transforming the fish from smooth and graspable into a rigid, bristling object that is difficult to bite, swallow, or manipulate. The spines distribute force across the predator's mouth, increasing discomfort and risk of injury with every attempt to clamp down. For predators that rely on a clean bite to disable prey, this sudden loss of control can be enough to trigger retreat. The physics of this transformation are as important as the visual effect. Inflation increases the fish's diameter far more than its mass, changing how force is applied during an attack. A predator that could easily crush or swallow the deflated fish now faces a target that exceeds its gape or presses outward against jaw muscles in ways that reduce leverage. Even predators capable of biting through bone must reassess the cost of continuing the attack when faced with an object that resists compression and threatens internal injury. The pufferfish does not fight back in the traditional sense. It forces hesitation by turning its body into a problem that must be solved under pressure. This hesitation is often all that is required. In the reef environment, where threats are numerous and opportunities fleeting, predators are tuned to abandon encounters that become uncertain or risky. The inflated pufferfish, awkward and immobile, does not need to escape immediately. It needs only to survive the initial assessment. Once the predator disengages, the fish can gradually expel the water it took in, deflating slowly and returning to its normal form once danger has passed. The entire sequence is reversible, allowing the fish to reset without permanent cost, provided inflation does not occur too frequently. Yet physical transformation alone does not tell the full story. Beneath the skin of many pufferfish species lies one of the most potent chemical defenses found in the marine environment. Tetrodotoxin, a neurotoxin capable of disrupting nerve signaling at extremely low concentrations, accumulates in the tissues of the fish, particularly in organs such as the liver, ovaries, and skin. This toxin does not originate within the fish itself, but is acquired through diet and symbiotic bacteria, illustrating a complex relationship between the animal and its microbial environment. The pufferfish becomes toxic not by manufacturing poison, but by integrating it into its biology through ecological interaction. For predators that have learned to recognize the consequences of biting a pufferfish, the inflated body serves as a visual warning backed by chemical reality. Bright coloration, bold patterns, or contrasting markings often accompany toxic species, broadcasting a message that transcends individual encounters. These warning colors, visible even in low light or turbid water, reinforce the lesson that the inflated form is not merely inconvenient, but dangerous. Predators that ignore this signal risk paralysis or death, a cost too high to justify experimentation. Over time, this dynamic shapes predator behavior across the ecosystem, reducing attack frequency not only on individual pufferfish, but on similar-looking species that benefit from shared recognition. The evolutionary trade-off embedded in this strategy is stark. Pufferfish sacrifice speed, endurance, and agility in favor of a defense that activates only under direct threat. This makes them vulnerable in environments where inflation is ineffective, such as narrow crevices or encounters with predators capable of attacking from angles that prevent full expansion. Inflation also carries physiological costs. Filling the body with water reduces mobility and oxygen availability, placing stress on internal systems that must be carefully managed. Repeated inflation events can be exhausting or even fatal if the fish cannot deflate quickly enough or is subjected to prolonged stress. To offset these risks, pufferfish adopt behavioral strategies that minimize exposure to danger. They often inhabit complex reef structures where line of sight is broken and predators must commit to close-range attacks. Their slow movement is paired with alertness and situational awareness, allowing them to detect threats early and prepare for inflation before contact is made. Some species exhibit cautious foraging behavior, limiting time spent in open water and retreating quickly to cover when disturbed. These behaviors reflect an understanding, embedded in instinct and experience, that their defense is powerful but situational. The presence of pufferfish influences the behavior of other species in subtle ways. Predators that learn to avoid them may shift hunting pressure onto alternative prey, altering local food web dynamics. Non-toxic species that resemble pufferfish in shape or coloration can gain a degree of protection through mimicry, benefiting from the reputation established by their toxic counterparts. This network of interactions demonstrates how a single defensive strategy can ripple outward, shaping community structure through perception and learning rather than direct competition. From a physiological perspective, the inflation mechanism represents an elegant solution to a specific survival problem. Instead of investing in constant readiness for flight or fight, the pufferfish concentrates its resources into a rapid response system that activates only when needed. Muscles, connective tissue, and organ placement are all arranged to accommodate extreme volume changes without compromising vital function. The fish's circulatory and respiratory systems must continue operating despite dramatic shifts in internal pressure, a feat made possible through flexible tissues and adaptive blood flow regulation. The toxin-based defense adds another layer of complexity. Tetrodotoxin interferes with sodium channels in nerve cells, preventing normal electrical signaling and leading to paralysis. For predators, even a small dose can impair swimming or breathing, making ingestion a potentially lethal mistake. The pufferfish itself is resistant to the toxin, its sodium channels modified to prevent binding, an adaptation that allows it to carry poison without self-harm. This resistance underscores the depth of specialization involved, as the fish's entire nervous system has been shaped to coexist with a compound that would incapacitate most other vertebrates. Despite this formidable arsenal, pufferfish are not invincible. Certain predators, including some sharks and specialized fishes, have evolved strategies to attack pufferfish in ways that avoid triggering inflation or minimize exposure to toxin. These predators may flip the fish to induce stress, attack from behind, or consume only non-toxic parts. Such interactions highlight the ongoing evolutionary dialogue between offense and defense, where no strategy remains unchallenged indefinitely. In ecological terms, pufferfish occupy a niche defined not by dominance, but by deterrence. They are not apex predators nor keystone species in the traditional sense, but their presence contributes to the complexity and stability of reef systems by shaping predator behavior and maintaining diversity. Their slow, deliberate movements contrast with the frenetic pace of many reef inhabitants, adding a different rhythm to the ecosystem that emphasizes patience over speed. The image of the inflated pufferfish, round and bristling, has become iconic, often portrayed as comical or exaggerated. This perception obscures the seriousness of the adaptation. Inflation is not a gimmick, but a survival system, refined through millions of years of selective pressure. It represents a shift from avoidance to confrontation, not through aggression, but through transformation. The pufferfish does not chase predators away. It convinces them that continuing the attack is a mistake. Seen in this light, the pufferfish embodies a different philosophy of survival, one that accepts vulnerability as a starting point and builds resilience through radical change. Its superpower is not speed, strength, or cunning, but the ability to turn its own body into an unmanageable object, a living fortress that buys time in moments of crisis. This strategy may appear passive, but it is anything but. It requires precise timing, complex physiology, and an intimate relationship with both environment and predator behavior. As the threat passes and the pufferfish slowly deflates, returning to its ordinary shape, the reef resumes its normal activity. The moment of transformation leaves no permanent mark on the landscape, only a memory encoded in the predator's experience and reinforced by warning signals carried forward through generations. In this quiet aftermath lies the true success of the inflation system. The pufferfish survives not by escaping unseen, but by being remembered, its altered form rewriting the expectations of those that would hunt it. In the end, the pufferfish reminds us that survival in the ocean is not always about outrunning danger. Sometimes it is about redefining it, forcing predators to confront a problem they are not equipped to solve. By turning its body into a fortress, the pufferfish demonstrates that power can emerge from transformation rather than confrontation, and that in the constant negotiation between predator and prey, the most effective defense may be the one that changes the terms of the encounter entirely. In the vertical forests of seagrass, mangrove roots, and soft corals where motion is constant and yet oddly predictable, the seahorse occupies a niche defined not by pursuit, but by patience. This environment is never still. Water flows in layered currents, plants sway rhythmically, and small animals drift, dart, and hover in patterns shaped by tide and wind. To survive here as a slow swimmer with no teeth, no claws, and no speed advantage requires a strategy built on precision rather than power. The seahorse does not chase prey through this moving maze. It waits, aligns, and strikes with a level of accuracy that turns stillness itself into a weapon. At first glance, a seahorse appears ill-suited for predation. Its upright posture creates drag, its tiny fins generate limited thrust, and its body is encased in bony plates rather than flexible muscle. Any attempt at pursuit would be futile against the quick reflexes of small crustaceans that share its habitat. Instead of evolving towards speed, the seahorse has refined a different solution, one that treats hunting as a problem of geometry rather than endurance. Its survival depends on reducing movement, blending seamlessly into the environment, and exploiting a brief moment when prey drifts within lethal range. Camouflage is the foundation of this strategy. Seahorses do not merely resemble their surroundings, they integrate into them. Skin filaments extend from the body to mimic algae or hydroids, while subtle color changes allow individuals to match the hues of seagrass blades, coral branches, or sponge-covered roots. These changes are slower and less dramatic than those of cephalopods, but they are precise and persistent, allowing a seahorse to remain visually unremarkable for extended periods. Remaining unnoticed is not about invisibility, but about being uninteresting, becoming another vertical element in a crowded field of similar shapes. The upright posture that seems awkward from a hydrodynamic perspective is central to this deception. By aligning its body with the vertical structures around it, the seahorse minimizes its silhouette and reduces visual contrast. Predators scanning horizontally across the habitat are more likely to overlook an object that blends into the dominant orientation of the environment. This same posture positions the seahorse perfectly for its method of feeding, turning its head into a stabilized firing platform rather than a flexible pursuit tool. The true weapon of the seahorse lies in its head and neck, which function as a biological spring-loaded system optimized for suction feeding. Unlike many fish that rely on jaw protrusion or rapid swimming to capture prey, the seahorse employs a lightning-fast head snap known as pivot feeding. In this maneuver, elastic energy stored in tendons is released suddenly, rotating the head upward in a fraction of a second. This motion aligns the tubular snout directly with the prey, creating a rapid expansion of the mouth cavity that generates a powerful vacuum. Water and prey are drawn in together, leaving the target no time to react. The speed of this strike is extraordinary relative to the seahorse's otherwise languid lifestyle. The head moves faster than muscle contraction alone would allow, relying on preloaded tension rather than active acceleration. This elastic recoil system mirrors those found in certain insects and crustaceans, where energy is stored gradually and released explosively. For the prey, typically small copepods or shrimp-like organisms, the attack is effectively invisible. One moment they drift with the current, the next they are inside the seahorse's mouth, captured without pursuit or struggle. Accuracy is paramount. The seahorse cannot afford missed strikes, as repeated attempts would reveal its presence and exhaust its limited energy reserves. To maximize success, it relies on a remarkable level of visual precision. Seahorses possess independently moving eyes, allowing them to scan their surroundings while remaining stationary. Each eye can track different targets, providing depth perception and motion detection critical for timing the strike. When prey enters the optimal zone, the seahorse subtly adjusts its body angle, often anchoring itself to vegetation with its prehensile tail to stabilize against current. This anchoring transforms the animal into a fixed platform, eliminating drift and ensuring that the strike occurs along a predictable trajectory. The prehensile tail is more than a grip. It is a stabilizing tool that compensates for the seahorse's weak swimming ability. By wrapping around seagrass blades or coral branches, the tail locks the animal into position, allowing it to hold steady even as water moves past. This stability is essential not only for hunting, but for avoiding detection. A drifting seahorse would stand out against anchored vegetation, while a stationary one disappears into the background motion of the habitat. Hunting in this way is energetically efficient. Rather than expending energy in continuous swimming, the seahorse invests in brief, high-impact movements that yield immediate returns. This efficiency is critical given the seahorse's limited capacity for oxygen intake and its reliance on small prey items that must be consumed frequently. By minimizing movement and maximizing strike success, the seahorse balances its energy budget within a narrow margin that allows survival in a competitive environment. Camouflage serves a dual purpose, protecting the seahorse from predators as well as concealing it from prey. Many animals that hunt visually rely on detecting motion or unusual shapes. The seahorse's stillness, combined with its plant-like appearance, exploits this reliance, reducing the likelihood of being targeted. Even when predators approach closely, the seahorse often remains unnoticed until it can reposition or retreat slowly into cover. This reliance on camouflage rather than flight underscores the animal's vulnerability, as any failure of disguise can be fatal. The stakes of survival are heightened by the seahorse's reproductive strategy, which places extraordinary demands on males. Unlike most vertebrates, male seahorses carry pregnancy, incubating fertilized eggs in a specialized brood pouch on the abdomen. This pouch regulates oxygen, salinity, and nutrient exchange, functioning in many ways like a placenta. During pregnancy, the male's mobility is further reduced, increasing reliance on camouflage and stable anchoring. The burden of carrying developing young transforms the male into an even more stationary target, reinforcing the importance of remaining hidden and minimizing risk. This role reversal has shaped seahorse behavior in subtle ways. Courtship rituals are elaborate but localized, often occurring in the same small area day after day. Mated pairs synchronize movements and color changes, reinforcing bonds that may last through multiple breeding cycles. This fidelity reduces the need for risky travel in search of mates, keeping individuals within familiar, well-camouflaged territories. Reproduction becomes an extension of the ambush lifestyle, favoring stability and predictability over exploration. The presence of pregnant males also influences predation dynamics. Predators that might otherwise learn to target seahorses encounter individuals that are particularly slow and encumbered, yet still difficult to detect. This reinforces selection pressure on camouflage quality rather than escapability. Over evolutionary time, this has produced seahorses that are masters of concealment, trading speed and aggression for subtlety and precision. Ecologically, seahorses play a modest but specific role. They regulate populations of small crustaceans, contributing to balance within seagrass and reef systems. Their reliance on structured habitats makes them sensitive indicators of environmental health, as degradation of seagrass beds or coral reefs removes both hunting platforms and camouflage opportunities. When these habitats decline, seahorses often disappear quickly, not because they are weak competitors, but because their entire survival strategy is built around environments that provide visual complexity and anchoring points. Migration in seahorses is limited, reflecting their dependence on localized habitat features. Most individuals remain within small home ranges, adjusting position only as conditions change. This lack of mobility makes recovery from population declines slow, as recolonization requires suitable habitat and connectivity. The seahorse's precision lifestyle leaves little room for improvisation, highlighting the costs of extreme specialization. Viewed through the lens of performance, the seahorse is not a passive drifter, but a highly tuned ambush predator. Its strike is as fast and decisive as any in the ocean, compressed into a moment that relies on alignment, timing, and mechanical advantage, rather than brute force. The contrast between its calm exterior and lethal capability embodies a recurring theme in marine evolution, where success often belongs to those who exploit physics and perception, rather than muscle alone. The combination of sniper-like feeding and male pregnancy underscores the seahorse's reliance on camouflage as its primary currency. Visibility equals vulnerability, and every aspect of its biology is shaped around reducing exposure. Color, texture, posture, behavior, and even reproductive roles align toward the same goal: remaining unseen long enough to feed and reproduce in a crowded, predator-rich world. As the seahorse waits among swaying plants, anchored and motionless, it becomes indistinguishable from its surroundings. Prey drifts closer, carried by currents that ignore danger. In a flash too fast to follow, the head snaps, the vacuum forms, and the target vanishes. The seahorse resumes its stillness, pregnancy pouch heavy, tail wrapped tight, life continuing in measured, deliberate moments. It does not dominate its environment through speed or strength, but through control of space, angle, and timing, proving that in the ocean, the most effective hunters are often the ones who never seem to move at all. In the shallow intertidal zones and deeper continental shelves, where tides scrape the seafloor clean and storms periodically reset the landscape, the starfish occupies a place that feels paradoxical. It is slow, soft, and often exposed, clinging to rock or sand in environments where crushing waves, sharp predators, and fluctuating temperatures leave little margin for error. Nothing about its movement suggests urgency, and nothing about its anatomy suggests resilience in the way armor or speed does. Yet the starfish persists through disturbances that erase faster, tougher organisms, surviving not by resisting damage, but by absorbing it and rebuilding afterward. Its strategy is not to avoid injury at all costs, but to redefine what injury means. To understand the starfish, one must abandon the idea of the body as a fixed structure. In most animals, the body is a closed system, a defined whole where loss of parts leads quickly to failure. The starfish operates under a different logic. Its body is modular, decentralized, and capable of reorganization in ways that challenge the boundary between individual and fragment. When a predator tears away an arm, the event is not necessarily fatal. In some cases, it is not even final. What looks like destruction becomes the beginning of a slow, resource-intensive process of reconstruction that unfolds over months or years, reshaping tissue, organs, and identity. Regeneration in starfish is not magic, and it is not instantaneous. It is a biological process rooted in cellular reprogramming, controlled growth, and metabolic trade-offs that carry real costs. When an arm is lost, the exposed wound seals quickly to prevent infection and fluid loss. But what follows is not rapid replacement. Cells near the injury site begin to de-differentiate, losing their specialized roles and returning to a more flexible state. These cells form a structure known as a blastoma, a region of proliferating tissue that serves as the foundation for regrowth. From this undifferentiated mass, new tissues emerge gradually, guided by chemical gradients and genetic instructions that map where muscle, nerve, tube feet, and skeleton must form. This process requires energy, and energy in the marine environment is never free. A regenerating starfish diverts resources away from growth, reproduction, and even routine movement to fuel cellular division and tissue organization. Feeding may continue, but efficiency often drops, as missing arms reduce the surface area available for locomotion and prey handling. During this period, the starfish exists in a state of compromise, alive but diminished, trading short-term performance for long-term survival. Regeneration succeeds not because it is fast, but because the starfish can endure slowness in environments where speed is not always decisive. Predation plays a central role in shaping this strategy. Many predators cannot consume a starfish whole, either because of its size, shape, or chemical defenses, but they can damage it. Fish, birds, and other invertebrates may tear away arms or inflict wounds that would be lethal to less flexible animals. In these encounters, the starfish may actively shed an arm, a behavior known as autotomy, reducing the immediate threat by sacrificing part of itself. The detached arm may continue to writhe briefly, distracting the predator, while the main body retreats or remains motionless until danger passes. This escape tactic only works because of what comes next. The starfish does not merely survive the loss, it plans for recovery. The ability to regrow an arm transforms predation from a terminal event into a temporary setback. Over time, the missing limb returns, complete with functioning tube feet, sensory structures, and skeletal elements. The regenerated arm may differ slightly in size or symmetry, but it restores the starfish's ability to feed, move, and interact with its environment. Survival here is not about avoiding harm entirely, but about enduring it better than competitors. In some species, regeneration crosses an even more radical threshold. Certain starfish can reproduce asexually by splitting their bodies, either intentionally or as a consequence of injury. An arm that contains a portion of the central disc, the region where vital organs converge, can regenerate not just a limb, but an entire new individual. This is the so-called two bodies trick, where what appears to be one organism becomes two through division and regrowth. The original body regenerates its missing parts, while the detached fragment reorganizes itself into a complete starfish, complete with mouth, digestive system, and radial symmetry. This form of cloning is not common across all starfish species, and it is not without cost. Producing two bodies from one requires enormous energy investment, and success depends on environmental conditions that support prolonged regeneration. Food availability, temperature stability, and absence of further disturbance all influence whether the process completes successfully. In harsh conditions, both halves may fail. Yet when conditions align, this strategy allows starfish populations to persist and spread even when sexual reproduction is limited or disrupted. The ecological implications of this ability are significant. Starfish are often important predators themselves, particularly of sessile or slow-moving organisms such as mussels, clams, and barnacles. Their feeding behavior can shape entire communities, opening space on rocky shores and influencing species composition. The capacity to regenerate ensures that starfish populations remain stable even under intense predation or environmental stress, maintaining their role as regulators within the ecosystem. Where starfish decline, the balance shifts, sometimes dramatically, as prey species overgrow available space and reduce biodiversity. Regeneration also interacts with the starfish's unique anatomy. Unlike animals with centralized brains and linear digestive tracts, starfish operate through a decentralized system organized around radial symmetry. Each arm contains extensions of the digestive system, nerve ring, and water vascular system, allowing it to function semi-independently. This decentralization makes regeneration feasible, as no single point of failure determines survival. When an arm regrows, it reconnects to existing systems rather than rebuilding them from scratch, integrating seamlessly into the whole. The water vascular system, which controls movement through hydraulic pressure in tube feet, is particularly important during regeneration. As new tube feet form, they must connect to this system to become functional, allowing the starfish to regain mobility and feeding capacity gradually. This stepwise return of function means that regeneration is not an all-or-nothing process. Even partial regrowth can improve survival prospects, increasing feeding efficiency and reducing vulnerability long before the arm is fully restored. The slow pace of regeneration reflects a broader pattern in the starfish's life history. Many species grow slowly, reproduce intermittently, and live for long periods, sometimes decades. This longevity supports a strategy where investment in repair outweighs investment in rapid reproduction. In environments where disturbance is frequent but not constant, such as intertidal zones battered by waves and predators, the ability to recover repeatedly can be more advantageous than producing many offspring quickly. The starfish becomes a specialist in persistence rather than proliferation. Temperature and metabolism further shape this process. In colder waters, cellular division and tissue growth proceed more slowly, extending regeneration timelines but reducing metabolic demands. In warmer waters, regeneration may occur faster but at higher energy cost, increasing reliance on abundant food sources. Climate variability therefore influences not only starfish distribution, but the effectiveness of their regenerative strategy, with cascading effects on the ecosystems they inhabit. It is important to recognize what regeneration does not do. It does not make the starfish invulnerable. Repeated injury can overwhelm its capacity to recover, and extensive damage to the central disc is often fatal. Disease, pollution, and temperature extremes can disrupt cellular processes essential for regeneration, turning a normally recoverable injury into a lethal one. The recent history of mass starfish die-offs associated with wasting diseases illustrates how fragile even resilient systems can be when environmental conditions shift beyond tolerable limits. Yet within those limits, regeneration remains one of the most striking adaptations in the marine world. It allows the starfish to occupy a niche where injury is common, but total destruction is not inevitable. It reframes the predator-prey relationship, reducing the finality of encounters and altering the calculus of risk. Predators may learn that attacking a starfish yields limited reward, while starfish continue to exert pressure on prey populations through sustained presence. The two bodies trick pushes this reframing even further. In these species, destruction and reproduction blur into the same process. Loss becomes multiplication, and survival becomes expansion. This challenges conventional definitions of individuality, forcing us to reconsider what it means to be one organism. When a fragment becomes a whole, the boundary between part and self dissolves, revealing a biological strategy built not on preserving form, but on preserving function across time. From a human perspective, regeneration often carries a sense of wonder precisely because it contradicts our own limitations. We are built to avoid injury because repair is incomplete and costly. The starfish lives by a different rule set, one where damage is expected and accounted for in the design of the body. This does not make the starfish superior, but it makes it instructive, highlighting how evolution can arrive at radically different solutions to the same problem of survival. In the shifting world of the seafloor, where disturbance is constant and certainty rare, the starfish endures not by outrunning danger or overpowering it, but by outlasting it. Its superpower is not immortality, but refusal to conform to the usual definition of death. Loss does not end the story. It initiates another chapter written slowly, cell by cell, arm by arm. As waves recede and predators move on, a damaged starfish clings to rock, its missing limb reduced to a scar that will soon swell with new growth. Time passes, tissue reorganizes, form returns. What was once a fragment becomes whole again, or in some cases becomes more than one. The seafloor keeps its memory poorly, but the starfish carries resilience forward in its body, a living record of survival through reconstruction rather than resistance. In the shallow tropical reefs, where sunlight fractures into wavering shafts and every surface seems alive with color and motion, the sea anemone stands rooted in place like a living trap disguised as a flower. Its tentacles sway with the rhythm of the water, soft and inviting in appearance, yet armed with microscopic weapons that make contact a lethal mistake for most creatures. Around it, fish move carefully, giving the anemone a wide margin of respect. This is a danger zone defined not by speed or pursuit, but by chemistry and touch. And yet, woven through these stinging arms, the clownfish moves freely, brushing against tentacles that would paralyze or kill any other fish within seconds. What unfolds here is not immunity by accident, but a negotiated alliance forged at the molecular level. The sea anemone is not a passive organism waiting for chance encounters. It is an active predator equipped with thousands of specialized cells called nematocysts, each a pressurized capsule containing a coiled harpoon tipped with toxin. When triggered by touch or chemical cues, these harpoons fire faster than most nerve impulses, injecting venom that disrupts cell membranes and nerve signaling in prey. Fish that blunder into anemone tentacles are immobilized almost instantly, their muscles seizing as toxins spread. The anemone then draws the prey inward toward its mouth, a slow but inevitable process once contact is made. This system is highly effective, allowing anemones to capture animals far larger and faster than themselves, compensating for their immobility with chemical precision. For most reef inhabitants, the anemone is a boundary rather than a refuge. Fish learn to recognize its shape and movement patterns, steering clear of its reach. Even brief contact can be fatal, and predators that attempt to attack anemones directly risk severe injury. The tentacles are not merely defensive, they define territory, creating a chemical perimeter that few species can cross. This makes the presence of the clownfish all the more remarkable. Rather than avoiding the anemone, the clownfish seeks it out, hovering at the edge before making deliberate, tentative contact. This introduction is not reckless. A clownfish does not simply dive into an anemone and hope for survival. Instead, it undergoes a careful acclimation process, touching the tentacles gradually, retreating, and repeating the behavior over time. Through this repeated exposure, the clownfish coats its skin in a specific layer of mucus that acts as a biochemical passport, masking the chemical signals that would normally trigger nematocyst discharge. This mucus is not generic slime, but a precise blend of compounds that either suppress the firing mechanism of the stinging cells or mimic the anemone's own chemical signature. The effectiveness of this mucus lies in the way nematocysts distinguish between self and non-self. Anemone tentacles do not fire indiscriminately at every touch. They rely on chemical cues to determine whether contact represents prey, threat, or self-tissue. By aligning its surface chemistry with that of the anemone, the clownfish essentially becomes invisible to the stinging system. The tentacles recognize the fish not as foreign, but as something that belongs within the anemone's chemical environment. This is not a permanent state granted at birth, but a maintained condition that depends on continued contact. If a clownfish is separated from its host for too long, the protective mucus layer can degrade, and re-entry becomes dangerous once again. This chemical truce is specific and selective. Not all clownfish can live with all anemones, and compatibility varies by species. Each pairing represents a finely tuned relationship shaped by evolutionary history, where mucus composition and nematocyst sensitivity align closely enough to allow coexistence. This specificity prevents exploitation by unrelated species and reinforces the stability of the partnership. The anemone tolerates the clownfish because it recognizes it chemically, and the clownfish survives because it has learned or inherited the means to negotiate that recognition. The benefits of this alliance flow both ways, transforming the anemone from a solitary predator into the center of a small but dynamic community. For the clownfish, the advantage is immediate and profound. Living among stinging tentacles provides near absolute protection from predators. Few fish are willing to risk contact with an anemone to pursue prey, and those that try often suffer severe consequences. The clownfish can retreat into the tentacles at the slightest hint of danger, disappearing into a zone that is effectively off-limits to attackers. This refuge allows the clownfish to occupy exposed reef areas it could not otherwise survive in, expanding its ecological niche. Protection, however, is only part of the exchange. The clownfish does not merely take shelter, it contributes to the anemone's success in subtle but important ways. By moving among the tentacles, the clownfish increases water circulation around the anemone's body, improving oxygen exchange and waste removal. This constant motion can enhance the anemone's respiration and overall health, particularly in calmer waters where stagnation might otherwise occur. The fish also removes parasites and debris from the tentacles, acting as a living maintenance system that keeps the anemone's weapons in optimal condition. Nutrient transfer adds another layer to this partnership. Clownfish excrete waste rich in nitrogen compounds, which are absorbed by the anemone and its symbiotic algae. These nutrients support the growth of zooxanthellae, photosynthetic microorganisms living within the anemone's tissues that provide energy through photosynthesis. In this way, the clownfish indirectly fuels the anemone's primary energy source, enhancing growth and reproduction. The anemone in turn grows larger and more robust, offering even better protection to its resident fish. The relationship becomes a feedback loop where mutual benefit reinforces stability. This alliance reshapes local predator-prey dynamics. Predators that might otherwise hunt small reef fish learn to avoid areas dominated by anemones, creating pockets of relative safety. These safe zones can influence the distribution of other species, altering feeding patterns and movement corridors across the reef. The presence of clownfish and anemones together thus has effects that ripple outward, subtly reorganizing space and risk within the ecosystem. What appears to be a simple two-species interaction becomes a structural feature of the reef landscape. The clownfish's behavior within the anemone reflects this security. Rather than remaining constantly alert and mobile like many reef fish, clownfish often exhibit boldness, venturing short distances away to feed before returning quickly to cover. This confidence allows them to exploit food resources that might be too risky for other small fish, further differentiating their niche. At the same time, their dependence on the anemone creates vulnerability. If the anemone dies or is removed, the clownfish loses its primary defense, becoming suddenly exposed in an environment filled with predators. Reproduction within this alliance adds complexity. Clownfish are protandrous hermaphrodites, meaning individuals begin life as males and can transition to females under specific social conditions. Typically, a dominant female and a breeding male share an anemone, with additional non-breeding males present. If the female dies, the breeding male changes sex and assumes the female role, ensuring continuity of reproduction without the need to search for new mates. This social structure reduces movement between anemones, reinforcing site fidelity and long-term stability of the partnership. Eggs are laid on hard surfaces near the base of the anemone, where the stinging tentacles provide additional protection from predators. The male guards and aerates the eggs, fanning them with his fins to ensure oxygen supply until they hatch. Even at this early stage, the alliance shapes survival, as eggs laid outside the anemone's protective zone would face significantly higher predation risk. The next generation enters the reef already linked to the chemical and ecological framework of the anemone relationship. The anemone, for its part, benefits from this reproductive activity through increased nutrient input and physical stimulation. The presence of multiple clownfish can enhance the anemone's growth rate and resilience, particularly in nutrient-poor environments. Some studies suggest that anemones hosting clownfish are larger and healthier than those without, indicating that the alliance has measurable physiological consequences. This mutual dependence underscores that the relationship is not incidental, but foundational to the life strategies of both organisms. Despite its effectiveness, the immunity deal is not invulnerable. Environmental stresses such as rising temperatures, pollution, and habitat degradation can disrupt the delicate chemistry underlying the partnership. Changes in water quality can alter mucus composition or nematocyst sensitivity, increasing the risk of stings even for acclimated clownfish. Coral bleaching events that affect zooxanthellae can weaken anemones, reducing their ability to support resident fish. In such cases, the alliance frays, exposing both partners to increased risk. From an evolutionary perspective, this relationship represents a departure from brute force solutions. The clownfish does not overpower the anemone's defenses, nor does the anemone disable the fish. Instead, both species adjust at the chemical level, negotiating a truce that allows coexistence in an otherwise hostile interface. This strategy is subtle, requiring precise molecular alignment rather than visible weaponry. It demonstrates that survival can hinge on compatibility rather than competition, and that alliances can be as powerful as armor. The visual contrast between danger and safety in this system is striking. To an outside observer, the anemone remains a lethal organism, its tentacles no less capable of delivering venom. Yet within those same tentacles, the clownfish moves calmly, immune to the threat that defines the anemone's identity. This duality reveals how context-dependent biological interactions can be, with chemistry determining outcomes that appearance alone cannot predict. In the broader reef ecosystem, the sea anemone and clownfish partnership stands as a reminder that not all defenses are physical, and not all power is expressed through force. Chemistry, recognition, and cooperation can rewrite the rules of engagement, creating safe havens in environments defined by risk. The superpower here is not immunity in the absolute sense, but negotiated tolerance, a fragile but effective agreement that benefits both sides as long as conditions allow. As currents shift and light fades toward evening, the clownfish retreats deeper into the tentacles, settling into a space that would be deadly to most life. The anemone continues its slow, patient sway, stinging cells armed and ready for any intruder that lacks the proper chemical credentials. Together, they form a living contract, written not in behavior alone, but in molecules, a chemistry-based alliance that turns one of the reef's most dangerous predators into a sanctuary.